Hello there and welcome to Physics with William, where curiosity settles in, science slows down a little, and even the strangest corners of the universe are allowed to arrive gently. Tonight, we are turning our attention to something very small, very short-lived, and oddly impolite. It is called the tau particle, and if particle physics were a tidy family album, the tau would be the relative in the back row making everyone slightly uncomfortable. Not because it is dangerous exactly, though you would not want one passing through your living room in any serious quantity, but because it raises a question that hangs over modern physics like an unpaid bill. Why is this thing here at all? Why does nature contain a particle that looks so much like an electron, behaves in many ways like an electron, belongs to the same little category as an electron, and yet arrives carrying an absurd amount of extra heft, only to disappear almost immediately? It is rather like ordering a simple biscuit and being handed a cast-iron frying pan shaped like a biscuit, still warm from some hidden kitchen of the cosmos. Before we get into that, I would love to know where you're listening from tonight, and what sort of hour has found you there. Perhaps it is late and the street outside has gone quiet. Perhaps the day is only just beginning where you are, and this is the universe easing its way into your morning. Maybe you are curled up under a blanket, or maybe you're doing something wonderfully ordinary, washing dishes, folding laundry, pretending to organise a desk that has long since given up being organised. Whatever your corner of the world looks like right now, I am very glad you are here. And if you find this soothing or interesting, or simply a pleasant way to let your thoughts drift while your ears stay busy, I would be very grateful if you liked the video and subscribed. It helps this quiet little space reach other people who might also enjoy hearing about the deep oddities of physics in a voice that is not trying to win a race. Now, I should warn you, this is one of those topics that sounds niche at first, and then becomes quietly unsettling. Because the tau particle is not just another piece of scientific trivia, not just a funny-sounding item from the menu of subatomic objects. It sits right in the middle of one of the most successful theories ever built, and yet it seems to ask, with some stubbornness, whether that theory has really told the whole story. The standard model of particle physics, which is the framework scientists use to describe the basic ingredients of matter and the forces that act on them, works astonishingly well. In laboratory after laboratory, decade after decade, it has passed tests with the kind of reliability most of us would be thrilled to see in a weather forecast, a printer, or an online parcel delivery window. It tells us about quarks and leptons and force carriers. It describes what electrons are doing around atoms. It explains how particles interact, combine, scatter, and decay. It is, by the standards of science, an extraordinary success, and yet, tucked inside it is a strange bit of repetition. Not once, but more than once, nature seems to have copied and pasted certain particles as if it briefly forgot it had already finished the assignment. The electron is one of those particles. It is familiar, stable, useful, and everywhere. Electrons help build atoms, chemistry, electricity, screens, lightning, nerve signals, and just about every practical thing you have ever blamed on a dead battery. If the material world had a dependable office worker, the electron would be there early with a folder in hand. Then there is the muon, which looks in many ways like a heavier version of the electron. Same electric charge, same broad category, same basic sort of behaviour, just more massive and much less willing to stick around. Already that is a little odd, but then, just when you think perhaps nature merely made one unnecessary duplicate and moved on, along comes the tau, bigger still, heavier still, less stable still. It is another member of the same family, another lepton, another particle that seems to be an electron in formal evening wear, except the evening wear is made of lead and it vanishes before the appetizers are served. This is where the discomfort begins. Physics does not mind strange things. In fact, physics rather expects them. Black holes are strange. Quantum uncertainty is strange. The fact that the universe allows empty space to behave like it is not quite empty at all is strange. But there is a difference between strange in a deep, elegant way, and strange in a rather suspicious way. The tau belongs more to the second category. It feels extra. It feels as though nature kept building versions of the same ingredient with different masses and neglected to leave a clear note in the margin explaining why. If you were designing a universe from scratch, and someone asked how many electron-like particles you would like, you might reasonably say 1, 2 if you were feeling extravagant, 3 begins to look less like design and more like someone in the cosmic workshop leaning on the copy button. And yet there it is, real, measured, produced in high-energy collisions, detected through the traces it leaves behind when it falls apart. The tau is not a rumour, not a speculative idea, not one of those lovely maybe objects that theorists invent on rainy afternoons and experimentalists spend 30 years trying to corner. It is as real as particle physics can make anything real. We know it exists. We know a fair amount about what it does. We know it belongs to the lepton family. We know it carries electric charge when we are speaking of the charge tau, and we know it has an associated neutrino because naturally the story was not already busy enough. We know it is much heavier than the electron and heavier than the muon too. We know it lives for a shockingly brief moment before decaying into other particles. We know it can appear in violent environments, in particle accelerators and cosmic events, briefly stepping onto the stage before promptly exploding into a smaller cast. There is something almost comical about that. Nature has gone to the trouble of creating a particle with an impressive mass, a complicated set of decay possibilities, and a full place in the official bookkeeping of matter, only to have it disappear so quickly that no atom will ever build its life around it. The tau does not make ordinary matter. It does not sit in your body helping hold your chemistry together. It does not orbit atomic nuclei in your coffee cup. It does not build rocks, lungs, copper wires, doorknobs, or spoons. It is not part of the quiet, stable furniture of everyday reality. It is more like a flash guest, arriving in the high-energy fringes of nature, proving that the universe contains more possibilities than daily life lets on, and then leaving the cleanup crew to sort through the fragments. So why should that bother anyone? After all, the universe is under no obligation to be minimal. It has never once promised a sufficiency. Stars explode with immense drama just to scatter ingredients that later become dust and bone and teeth. Galaxies collide on timescales so vast that even the word schedule starts to feel optimistic. Perhaps having a heavy, fleeting cousin of the electron is simply part of the deal. But physicists are not bothered by the tau because it is wasteful in some moral sense. They are bothered because repeated patterns usually hint at underlying rules, and the rule here remains annoyingly opaque. Why these 3 generations of matter? Why the light one, the heavier one, and then the much heavier one? Why the same charges and interaction pattern, with masses that seem to have been assigned by a committee that adjourned before finishing its explanation? If there is a deep organising principle here, we have not fully caught it in the act. One of the most revealing habits in science is the habit of asking not only what exists, but what had any business existing in the first place. That sounds rude, but it is one of the best tools we have. We ask why there are planets and not just dust. We ask why atoms hold together. We ask why the speed of light has the value it has, why gravity is so feeble compared with other forces, why neutrinos are so absurdly light, why antimatter is not sitting here in equal abundance ruining everybody's lunch. The tau enters that tradition very naturally. It makes us ask whether the standard model is a final list, or just a carefully written summary of a deeper arrangement. Maybe the tau exists because there are layers of physics beneath the one we currently use, and the 3 generations of particles are like 3 clues in plain sight. Or maybe nature simply has a taste for repetition, though scientists tend to become suspicious when repetition arrives without explanation. To get a feel for the tau, it helps not to imagine a tiny billiard ball, because particles are never as tidy as that. They are excitations of underlying fields, which is a very proper and accurate way of saying that what we call a particle is not a little bead rolling through space, but a localized event in something more fundamental. Still, human brains like handles, and a billiard ball at least gives the fingers something to grab. So for the moment, picture the tau as a heavy cousin of the electron, charged in the same way, but carrying much more mass and possessing a life expectancy so poor that it makes a soap bubble look committed. If the electron is a steady candle on the table, the tau is a spark from the fireplace, bright, real, undeniable, and gone before you have quite decided whether you saw it properly. That vanishing act is part of what makes the tau such a challenge. Electrons are wonderfully cooperative. They hang around. They form atoms. You can trap them, guide them, accelerate them, and blame them for static electricity when your clothes misbehave. Taus are not like that. A tau is born in energetic processes and almost immediately decays into something else. It can decay in several different ways, producing lighter particles that experimental physicists then have to reconstruct, with all the calm patience of detectives arriving after the suspect has already jumped out the back window. One does not really see a tau in the sense one sees a stable object. One infers it from the wreckage, from the pattern of daughter particles, from energy and momentum and timing and tracks in a detector that together whisper, very briefly, a tau was here. There is a certain detective story quality to particle physics that I think often gets overlooked. We like to picture great machines smashing particles together, and yes, those machines are real and magnificent and expensive enough to make a household budget faint. But the deeper work is interpretive. It is forensic. A collision takes place, a spray of particles flies outward. Some leave tracks, some deposit energy, some vanish into invisibility and have to be inferred from what is missing. The tau belongs beautifully to this world of inference because it refuses to stay put. It is one of those entities that reminds us physics is often less about watching objects behave like obedient marbles and more about reconstructing a story from a chaotic scene. And the story the tau keeps inserting itself into is one with a strangely recurring line. Here is another lepton. Here is another heavier version. Here is another sign that the pattern is not as simple as one might have hoped. That is why the tau becomes more interesting the longer you look at it. At first, it sounds almost like a specialist detail, something for particle physicists in windowless offices, and people who genuinely enjoy diagrams of decay channels. But then its existence starts leaning outward into bigger questions. Why do particles have the masses they do? Why are there families at all? What determines which particles become stable ingredients of matter and which appear only fleetingly in violent events? Is the tau merely the third item in a list, or is it evidence of a deeper structure we have only partially mapped? You can think of it a little like finding 3 keys on a ring when you only know what one door does. The first key you understand, the second makes you curious, the third makes you suspect the house is much larger than you were told. There is also something quietly humbling in the fact that ordinary reality has almost no use for the tau. We spend our lives surrounded by matter built from a small, stable subset of nature's possibilities. Protons and neutrons in nuclei, electrons arranged around them, light passing through, forces holding things together. We could easily mistake that narrow slice for the whole menu. But the tau reminds us that the universe contains possibilities far beyond the ingredients required to make cats, coffee mugs, trees, pillows, and mildly disappointing toast. There are particles that seem almost unnecessary from the perspective of daily life, yet they are built into the underlying grammar of matter all the same. The universe is not written just for our convenience. It is larger, stranger, and less edited than that. If all of this sounds a little unfair to the tau, as though we are being mean to a perfectly respectable particle for having turned up overdressed, I should say in its defense that the tau is not only a problem, it is also a tool. Precisely because it is heavy, and because it interacts in ways that let physicists test subtle parts of the standard model, it becomes a sensitive probe of deeper physics. Tiny discrepancies in how taus are produced or how they decay can hint that something beyond the standard model is tugging at the numbers. In that sense, the tau is not just an oddity sitting on the shelf. It is an instrument, a pressure point, a way of asking the universe whether its neat official account is missing a page or two. That is one reason scientists care so much about it. The tau may be short-lived, but it has a knack for making long conversations necessary. And perhaps that is the right way to begin our story, not by treating the tau as a random curiosity, but by noticing that it occupies a very particular role. It is both a member of a family and a challenge to the meaning of that family. It is familiar in shape, unfamiliar in mass, and inconveniently temporary. It resembles the electron enough to make comparison irresistible, but differs enough to make that comparison uncomfortable. It lives at the point where repetition becomes mystery. That is always a good place for physics to start, because science is often less about things being strange in isolation, and more about things being almost understandable, almost orderly, almost sensible, until one detail refuses to sit still. So as we settle into this question of what a tau particle really is, it helps to keep two thoughts in mind at once. First, the tau is not some loose extra floating outside the established picture. It belongs squarely within the standard model, with a place in the official roster and a long history of experimental study. Second, its very presence in that picture is one of the reasons the picture still feels incomplete. The tau is both accounted for and unexplained, described but not fully justified, catalogued but not entirely understood, and that peculiar combination is what gives it its charm. It is not a crack in physics exactly, but it is certainly the sort of seam one presses on to see whether the wall behind it is hollow. In a moment we're going to widen the view a little and look at the family portrait of matter itself, because the tau makes far more sense once you see the company it keeps. The electrons, the quarks, the neutrinos, the repeated generations, the odd little structure of the standard model that looks efficient in one light and faintly suspicious in another. That larger setting matters, because the tau is not weird just by itself. It is weird in context. And context, as physics so often reminds us, is where the real trouble begins. When physicists talk about the basic ingredients of matter, they are not talking about atoms in the way most of us first learned about them at school, with little electrons circling a nucleus like loyal planets in a very tidy solar system. That picture is useful for a while, and then, like many useful things, it begins to wobble under closer inspection. The deeper story is less neat, more crowded, and in some ways more peculiar. Underneath atoms, underneath chemistry, underneath solids and liquids and living tissue, and the thin glass screen you may be looking at right now, there is a roster of particles that modern physics treats as fundamental. Not fundamental in the sense that we are absolutely certain nothing lies below them, because science becomes nervous when anyone uses the word absolutely for too long, but fundamental in the sense that, as far as present experiments can tell, these particles are not made of smaller known pieces. They are the alphabet from which ordinary matter is written, though like any alphabet designed by the universe, it contains a few letters that seem to appear far less often than one might expect, and one or two that look suspiciously like duplicates of others. This is where the family portrait becomes useful, because the tau is much easier to appreciate or to distrust once you see where it sits. The standard model arranges the basic matter particles into a set of families. There are quarks, which combine to make larger things like protons and neutrons. There are leptons, which include the electron and its more elusive relatives. Then there are the particles that carry forces, like the photon for electromagnetism, and others for the nuclear forces. It is a structure that is, on the surface, almost elegantly bureaucratic. Everything has a place. Everything has a role. It looks as though some cosmic filing cabinet has been very carefully labelled. Yet the longer one stares at that filing cabinet, the more certain drawers start to feel strange. Not broken exactly, but overstocked in ways nobody has properly justified. Take the quarks first. There are 6 of them in total, arranged in pairs across 3 generations. Up and down form the first generation, charm and strange the second, top and bottom the third. Their names sound less like the bedrock of existence, and more like the result of a distracted committee being allowed to continue work after lunch. But despite the names, quarks are serious business. They carry a property called color charge, which has nothing to do with visible color and everything to do with the strong nuclear force, the interaction that binds them together into composite particles. Protons and neutrons, the stuff at the heart of atoms, are built from up and down quarks. Those are the familiar labourers of ordinary matter. The others exist too, but they tend not to settle into the long-term furniture of daily life. They show up in energetic processes, in particle collisions, in unstable states, and then they transform or decay. Already there is something a little suggestive here. The first generation contains the particles you need to make the world as we know it. Up quarks, down quarks, electrons, and electron neutrinos. That is enough to construct atoms, chemistry, stars, people, bread, rain, regret, and all the rest of it. If nature had stopped there, physics would still have had plenty to do. It would not have been a simple universe. Gravity would still curve space-time. Quantum mechanics would still challenge intuition. Light would still behave in that half-wave, half-particle way that makes undergraduates look personally betrayed. But at least the menu of matter would have been concise. Instead, nature did not stop there. It went on to produce a second generation and then a third, each one echoing the first in structure, while differing mainly in mass and instability. That is the part that makes physicists begin to narrow their eyes. Leptons show this pattern with particular clarity. In the first generation, there is the electron and the electron neutrino. In the second, the muon and the muon neutrino. In the third, the tau and the tau neutrino. So there it is, right in the official architecture. The tau is not some intruder. It is part of a repeating pattern. The question, of course, is whether repeating the pattern explains anything, or merely restates the mystery in a more organised format. Because once you lay it out that way, the oddity sharpens. Why do we have these three versions? Why one light-charged lepton that is stable and indispensable, then another heavier one that decays, then a heavier still one that decays even faster? Why corresponding neutrinos for each? Why not one generation? Why not 4? Why exactly this arrangement? If you are new to all this, it may sound as though perhaps the second and third generations are simply more advanced, or more energetic versions of the first, like upgrades in a product line. But physics is not quite that accommodating. The heavier generations are not needed to build ordinary matter. They are not later improvements. They do not add obvious everyday functionality. They resemble their lighter cousins in charge and interaction pattern, but differ dramatically in mass, and mass matters a great deal. Mass influences how particles behave, how they are produced, how they decay, and what role they can play in the world around us. An electron can exist peacefully for as long as the universe allows. A tau cannot. A proton can sit quietly in a hydrogen atom for billions of years. A top quark lasts for such a vanishingly brief interval that calling it short-lived almost feels insulting to the concept of life. That is why the family portrait is both beautiful and irritating. Beautiful because the structure is so regular. Irritating because regularity usually tempts us to think we understand the underlying rule, and here the rule remains incomplete. The three generations line up almost as if they were designed to reassure us. Same charges, same broad kinds of particles, similar interaction patterns. Yet the masses jump around in a way that feels more like a list of outcomes than a list of reasons. The electron is light. The muon is much heavier. The tau is heavier still. The up quark is light. The charm is heavier. The top is absurdly heavy. Nature has repeated the forms, but not in proportions that give away an obvious blueprint. It is a little like finding 3 sets of cutlery in a drawer, one tiny, one medium, one the size of gardening tools, and being told not to worry, there is surely a system. It helps here to pause and appreciate what the standard model does and does not do. It does tell us how particles interact. It tells us how the electromagnetic force works through photons, how the weak force operates through its own carriers, and how the strong force binds quarks. It allows physicists to calculate scattering probabilities, decay rates, cross-sections, and all sorts of things that sound intimidating until you realise they mostly amount to asking how likely particles are to do particular strange little dances when given the chance. The model is excellent at that. It is one of the most successful predictive frameworks in all of science. But success of that kind can sometimes hide an awkward truth. A theory may describe the behaviour of its ingredients brilliantly, without fully explaining why those ingredients are the ones on the list. The standard model is in that position. It gives us the cast and their lines. It does not fully tell us why the play has this cast rather than another. And that matters for the tau, because the tau is a perfect example of a particle that is accounted for in one sense and unexplained in another. Its properties can be measured, its interactions can be calculated, its place in the third generation is clear. But why there should be a third generation at all, and why the tau should occupy it with precisely that heft and instability, remains unsettled. When scientists say a particle should not exist, they rarely mean that it breaks the current equations by simply showing up. They mean something subtler and more philosophical. They mean that its existence feels unjustified by the deeper logic we had hoped nature would reveal. The tau should not exist in the sense that once you realise the first generation is enough to make the visible world, the additional copies begin to look suspiciously extravagant. There is another way to see the weirdness. Imagine a carpenter building a chair. One leg is necessary, another is necessary. Soon, all four are in place and the chair stands. Then, for reasons known only to the carpenter, he begins producing additional chair legs, each one made of stranger wood, each one heavier than the last and none of them actually attached to the chair. You would not say the extra legs are impossible. Clearly they are there on the workshop floor. But you would be entitled to ask what exactly the carpenter was trying to do. The standard model has a little of that feeling. The first generation builds the ordinary world. The others appear more like spare pieces, except they are not actually spare, because their existence affects high-energy processes and may reveal deeper physics. They are unnecessary for the chair, perhaps, but very important for understanding the workshop. The neutrinos complicate the picture in an especially mischievous way. For each charged lepton, there is a corresponding neutrino: electron neutrino, muon neutrino, tau neutrino. Neutrinos are ghostly particles, neutral in charge and astonishingly reluctant to interact with matter. They pass through planets the way most of us pass through a patch of sunlight, barely noticing anything. For a long time, physicists thought neutrinos might be massless. Then it turned out they have tiny masses after all, and, in one of the most quietly disruptive findings in modern physics, they can change identity as they travel. An electron neutrino can later be detected as a muon neutrino or a tau neutrino. That phenomenon, called neutrino oscillation, tells us that the standard model in its simplest original form is not quite complete. Even the shyest particles in the portrait are apparently rearranging their name tags behind our backs. This matters because it suggests that the family structure may run deeper than we first thought. The generations are not merely stacked like identical shelves. There is mixing. There is transformation. Quarks, too, can shift their flavour in certain interactions, with probabilities governed by a pattern that is measurable but not fundamentally explained. The family portrait, then, is not a static yearbook. It is more like a household in which relatives keep exchanging hats. Some of them are vastly heavier than others for no stated reason, and a few vanish almost as soon as they enter the room. It works, astonishingly, but it is not the sort of arrangement one would call intuitively satisfying. That lack of satisfaction is important. Science is not obliged to gratify human taste, and physicists know this better than most. Nature has repeatedly refused to align itself with common sense. But there is a difference between accepting strangeness and giving up on pattern. Repeated structures often hint at some hidden organizing principle. The periodic table, before quantum mechanics fully explained it, was already whispering about a deeper order in chemistry. Spectral lines in atoms hinted at quantized energy levels before the full theory arrived. So when particle physics presents us with 3 generations of matter, almost like 3 verses of the same song sung at different pitches, it is hard not to suspect that something more fundamental is waiting underneath. The tau, as the heaviest charged lepton, becomes an especially sharp expression of that suspicion. Notice too how ordinary life hides all of this. The desk, the walls, the bones in your hand, the air moving in and out of your lungs, all of that is built from the mild-mannered first generation. The second and third generations are not strolling around in permanent residence. Their particles appear in energetic environments, in cosmic ray showers, in accelerator experiments, in the very early universe, and in fleeting quantum processes. That means daily experience offers no intuitive picture for them. We do not grow up surrounded by taus the way we grow up surrounded by electrons. We do not feel the quiet presence of muons in household chemistry. These particles belong to a more extreme register of reality, one that only becomes visible when nature is pressed hard enough or looked at with machines of extraordinary sensitivity. And yet their absence from daily life does not make them unimportant. Quite the opposite. Their very uselessness to ordinary matter is what makes them scientifically provocative. If the world can get by perfectly well without stable taus, why are taus in the laws of nature at all? Why was the universe not written more economically? Perhaps because economy is not the right standard. Perhaps the deeper theory, whatever lies beyond the standard model, generates these families naturally, and what looks redundant to us is merely a side effect of a more beautiful structure we do not yet see. That is often how science works. What first appears wasteful later turns out to be inevitable once the larger framework is understood. But until that larger framework arrives, the family portrait continues to look faintly overcomplicated. It is also worth noticing that mass itself is one of the least satisfying entries in the whole picture. The standard model includes a mechanism connected to the Higgs field that allows particles to acquire mass, and the discovery of the Higgs boson was a triumph because it confirmed a crucial part of that story. But knowing that particles get mass through interactions with the Higgs field is not the same as knowing why different particles get the particular masses they do. Why the electron has its modest value, why the muon is heavier, why the tau is heavier still, why quark masses span such an enormous range, those questions remain open at a deeper level. The theory contains parameters that must be measured from experiment. It does not yet derive them from first principles in a fully satisfying way. So even in the official portrait, the labels under each face are partly descriptive rather than explanatory. This is another reason the tau feels so provocative. It sits at the intersection of 2 kinds of mystery. One is the mystery of generations, the repeated families of matter. The other is the mystery of mass, the bewildering pattern of values assigned across those families. The tau is not the heaviest particle overall, but it is the heaviest charged lepton, and that makes it a particularly clean case. Unlike quarks, which are permanently confined inside larger particles and tangled up with the strong force in messy ways, the 2 belongs to the lepton family, where the interpretive clutter is somewhat reduced. It is still complicated, but in a way that lets physicists test important principles with unusual precision. In that sense, the tau is a kind of ideal suspect. Strange enough to be interesting, but not so entangled that the clues become unreadable. If all this sounds a bit severe toward the standard model, I should be fair and say that one of the most remarkable features of modern physics is how far this model has taken us. It predicted particles before they were found. It accounted for interactions across astonishing ranges of energy. It survived countless experimental checks. It is not a flimsy or temporary scaffold, it is an extraordinary structure. The frustration comes precisely because it is so good. A bad theory can be discarded without heartbreak. A very good theory that still leaves deep questions unanswered is much harder to sit with. It creates a special kind of scientific restlessness, the sense that one is standing in a beautifully furnished house, while still suspecting that a door behind the wallpaper leads to rooms no one has properly mapped. In that house, the family portrait hangs in a prominent place. 3 generations of quarks, 3 generations of leptons, force-carrying particles mediating interactions, the Higgs field helping shape the masses, everything in formal arrangement, and then there is the discomfort of redundancy. Why this repetition? Why these values? Why does the first generation make the material world while the others seem to exist as heavier, more fleeting echoes? If the universe were a novel, one might think these characters introduced for a reason not yet revealed. If it were a bureaucracy, one might suspect historical paperwork no one had the courage to throw away. Physics, annoyingly, permits neither interpretation without evidence. Still, the picture does give us something precious. It gives us context. The Tau is not weird because it is isolated. It is weird because it is the third member of a pattern that is itself mysterious. Without the family portrait, the Tau might seem like a random heavy particle among many. With the portrait in view, it becomes something more specific and more unsettling. It is the final charged lepton in a 3-part repetition that nature has offered without full explanation. It is the point at which one stops saying, well, perhaps there is just one unnecessary cousin, and starts saying, no, there is definitely a structural story here, and we do not yet know the ending. That is the frame we need before going any further, because the next step is to look more closely at the T not merely as a box in a table, but as a specific kind of particle, one whose resemblance to the electron is as important as its enormous difference in mass. Once that comparison sharpens, the whole mystery becomes more personal. The Tau stops being just one face in the portrait and starts becoming the relative who looks uncannily familiar until you realise something is profoundly off. That sense of familiarity is really the key. The Tau is unsettling not because it belongs to some completely alien category of matter, but because it looks so much like something we already know. If you were handed the basic description without the mass attached, you might think someone was simply talking about the electron again. The Tau carries the same electric charge. It belongs to the same lepton family. It responds to the electromagnetic force in the same broad way. It also takes part in the weak interaction, just as the electron does. In the accounting system of the standard model, it sits in the same sort of box, wearing much the same badge, following much the same set of formal rules. And then you reach the line where the mass is written down and the whole mood changes. The Tau is not just a little heavier than the electron, it is dramatically heavier, so much heavier that the resemblance begins to feel almost rude. It is as though nature introduced a familiar character, and then quietly replaced the shoes with anvils. This is why it helps to think of the Tau as a heavy twin, though even that phrase is slightly too polite. Twins are usually expected or at least tolerated. The Tau feels more like the duplicate no one ordered, the extra item in the parcel that leaves you checking the invoice. The electron makes sense to us very quickly. It is stable. It helps build atoms. It belongs to everyday matter. It is woven into chemistry and electricity and all the ordinary processes that make a world feel solid and inhabited. The muon already complicates that picture by appearing as a heavier copy that does not stick around. Then the Tau arrives and pushes the whole idea further still. It is not content merely to be another version. It is a much heavier version, a short-lived version, a version that exists just long enough to force awkward questions and then vanishes before anyone can demand a proper explanation. What makes this especially strange is that, on paper, the Tau is not exotic in the way people often imagine particle exotica. It is not carrying some bizarre charge unknown to ordinary matter. It is not invented to patch over one highly specific anomaly. It is not one of those speculative particles that people invoke when they want to explain dark matter, dark energy, or whatever else happens to be worrying cosmology that month. The Tau is official. It is established. It belongs to the core furniture of the standard model, and yet its existence still carries the faint air of an administrative error. because it duplicates so much of what the electron already does while adding no obvious benefit to ordinary reality. If electrons are enough to make atoms, chemistry, and the visible world, why is there a bulked-up cousin with the same charge and same category, but no steady role in daily matter? One answer, of course, is that the universe does not owe us utility. It is not a product line designed around household convenience. The cosmos has never once said that every ingredient must justify itself to human common sense. Still, scientists are allowed to be suspicious when nature repeats itself with no clear reason. Repetition in physics can mean symmetry, and symmetry can be a clue. It can also mean there is a deeper mechanism generating a family of related particles, whether or not the visible world needs them. That is often how the Tao is treated, as evidence that the standard model is not really the final explanation, but the visible surface of something deeper. The Tao may be the third charged lepton in a neat row, but neat rows in physics are rarely the end of the story. They're usually the start of a more difficult one. To see why the comparison with the electron matters so much, it helps to slow down and ask what physicists mean when they say two particles are of the same kind in some respects. The electron and the Tau are both leptons, which means they are matter particles that do not feel the strong nuclear force. They are both charged leptons, which means they carry electric charge and therefore interact with light in the broad sense governed by electromagnetism. They both have a property called spin that places them in the class of particles from which matter is built. They both come with corresponding neutrinos. They both fit into the weak interaction in related ways. If you drew up a comparison sheet of their quantum identity cards, many of the entries would line up rather neatly. It is not as though the Tau is unfamiliar in every dimension. In several of the most important categories, it is deeply familiar, and yet mass is not some decorative extra detail. Mass changes the entire practical meaning of a particle. It affects how easily the particle is produced, what sorts of processes it can participate in, how quickly it decays if decay is available, and whether it can appear as a stable building block of matter. The electron is light enough and protected in the right ways to remain stable. The Tau is so heavy that nature can take it apart through the weak interaction into lighter particles. That means the Tau never settles into the lasting architecture of ordinary matter. It flashes into existence in energetic events and then falls apart. So the comparison is uncanny. Same family, similar formal role, vastly different practical fate. It is like meeting two relatives with the same surname, same eyes, same voice, and discovering that one lives quietly in the village while the other arrives on a motorcycle, sets off 3 alarms, and disappears before dessert. This is where the phrase "nobody asked for" begins to feel justified. It is not that physicists are offended by the Tau, far from it. They are fascinated by it. But if one were designing the minimal set of particles required to build a world much like ours, the Tau would not make the shortlist. The electron would remain. Up and down quarks would remain. Neutrinos in some form would probably remain, though they are mysterious enough to make any such list feel rash. The photon and the force carriers would remain. But a very heavy charged lepton that lives for only a tiny fraction of a second would not look essential. The Tau is one of those features that reminds us physics is not the art of inventing what seems necessary. It is the art of discovering what nature actually contains, whether or not it fits our tidy instincts. There is also a psychological reason the Tau feels stranger than some of the heavier quarks. Quarks are already a little difficult for intuition. They are never found alone. They are confined inside composite particles. They carry the strong interaction with all its messy and demanding behaviour. The Tau is cleaner. It belongs to the lepton family, where comparison with the electron is almost irresistible. You can see the family resemblance too clearly. That makes the differences stand out with more force. A top quark is spectacularly heavy, but it lives in a part of the particle world that already feels dense and complicated. The Tau, by contrast, sits right next to the electron in the conceptual filing cabinet. That nearness is what gives it its special unease. It is the familiar face with the impossible weight. Imagine for a moment that ordinary matter were built from taus instead of electrons. the universe would look very different. Chemistry as we know it would not survive. Stable atoms arranged in the familiar way would not form. The gentle architecture that allows molecules to persist, react, and organize into complex structures would be gone. The tau simply does not stay around long enough. It is too heavy and too unstable to play the role the electron plays with such patient competence. That contrast tells you something important. The electron is not just one option among many. It is the specific charged lepton that can actually build a lasting world. The muon and tau are more like shadow versions of that possibility, echoing the form without sharing the function. They are copies in the legal sense, perhaps, but not in the domestic one. And this raises a deliciously annoying question. If only one charged lepton is needed for stable matter, why are there three? Why did nature not stop with the useful one? Why add the muon and then the tau? Physicists have lived with this question for decades, and while there are many ideas, no single answer has fully settled the matter. Some deeper theories suggest that the three generations may emerge naturally from hidden symmetries or from the way matter fits into larger mathematical structures. Others hint that what looks redundant at low energies may be inevitable at higher ones. There are even ways of thinking in which the family pattern is not an afterthought, but a central clue to how the universe organizes itself. Still, the plain fact remains. We have the electron, we have the muon, and then we have the tau, and the third one feels very much like the point at which repetition stops being a curiosity and becomes a demand for explanation. The tau also sharpens another discomfort in particle physics, namely that mass values themselves are not deeply explained by the standard model. The theory allows particles to acquire mass through their relationship with the Higgs field, but the specific strengths of those relationships are not predicted from some simple, underlying principle. They are measured. They are input. The theory then uses them brilliantly. This is a bit like being handed a cookbook that perfectly explains how ingredients behave when mixed and heated, while refusing to say why your pantry contains exactly those ingredients in exactly those amounts. Very practical, very successful, and still slightly maddening. The electron has one mass, the muon has a much larger one, the tau has a larger one still. The question is not whether the theory can work with those values. It can. The question is why nature chose them. One of the most helpful ways to appreciate the tau is to separate similarity from consequence. Similarity tells you why it belongs next to the electron in the family tree. Consequence tells you why that similarity is misleading if taken too far. In a very abstract sense, the tau behaves like a heavier electron. But heavy is doing an absurd amount of work in that sentence. Heavy turns a stable component of matter into a transient one. Heavy changes accessible reactions. Heavy opens decay routes. Heavy makes the particle much harder to produce in ordinary conditions. Heavy prevents it from quietly settling into atoms and sticking around long enough to become part of tables, planets, lungs, or teacups. So yes, the tau is like an electron, but only in the same way a cannonball is like a snowflake, if all you mention is that both fall downward. This is where gentle humour becomes almost necessary, because the alternative is to stare too long at the absurdity of the arrangement. Nature has created a charged lepton so hefty that it can disintegrate into a small parade of lighter particles, then placed it in a family whose most famous member spends its days holding atoms together and helping your kettle turn electricity into disappointment when you forgot to refill it. The electron feels domestic. The tau feels theatrical. The electron minds the house. The tau bursts through the wall, announces itself with impeccable credentials, and then collapses into other guests before anyone has found a clean cup. And yet the theory insists they are related in the deepest formal sense. That relation matters experimentally. Because the tau is so heavy, it can couple more strongly in certain contexts where mass matters. It becomes a useful place to look for subtle deviations from standard model expectations. If new physics lurks beyond the established theory, It may reveal itself through the behaviour of heavy particles more readily than through light ones. The tau is therefore not merely an inconvenience, it is a probe. It gives physicists a way to test whether electrons, muons and taus truly behave as the standard model says they should, aside from the differences demanded by mass. If one member of the family begins acting strangely, that could be a sign of deeper cracks in the theory. In that sense, the heavy twin nobody asked for may turn out to be the one relative who notices the house is built over a hidden cellar. There is another angle from which the tau becomes almost endearing. It reminds us that the universe is not built solely around the conditions that make everyday life possible. We are tempted quite naturally to think of the useful, stable particles as the central cast and the fleeting ones as decorative extras. But from the point of view of the laws themselves, that may be a parochial view. The early universe was vastly hotter and more energetic than the present one. High-energy collisions in cosmic rays and accelerators routinely produce particles that ordinary room temperature life never encounters in a sustained way. The tau belongs to that wider register of reality. It tells us that the laws of nature contain possibilities far beyond the calm subset needed for chemistry and biology. Its uselessness to household matter is not evidence of irrelevance. It is evidence that the universe is broader than the portion we can comfortably live inside. Still, breadth alone does not dissolve the puzzle. The central discomfort remains. The tau resembles the electron too much to feel accidental, and differs from it too much to feel trivial. It is precisely balanced between familiarity and excess. If it were completely alien, we would accept it as another strange species in the zoo. If it were only slightly heavier, we might shrug and move on. But the actual tau sits in a sweet spot of scientific irritation. Familiar charge, familiar category, wildly different mass, no obvious everyday purpose. That combination compels attention. It is the sort of detail that makes theorists fill notebooks and experimentalists build detectors the size of buildings. We should also be careful not to let the language of duplication fool us into thinking the tau is merely a redundant electron with extra weight bolted on. It is its own particle. It has its own role in the weak interaction. It has its own neutrino partner. Its decays open windows into parts of the theory that lighter particles cannot access in the same way. In precision studies, the two becomes a laboratory for testing how universal the laws really are across the 3 lepton generations. The standard model says that, apart from mass effects, the charged leptons should be treated equally by the underlying interactions. This idea, often called lepton universality, is one of the quiet structural promises of the theory. The tau therefore becomes a very stern examiner. If the universe treats it even slightly differently in ways that cannot be blamed on mass, that would be a clue of enormous importance. So perhaps nobody asked for the tau, but physics has learned to be grateful for uninvited guests. Again and again, the particles that seemed unnecessary at first have ended up teaching us something central. The muon once inspired the famous complaint about who ordered that. The tau could inspire the same remark with even more justification. But the deeper lesson is that nature is under no obligation to reveal its logic in the order we would prefer. Sometimes the strange extra appears first as an inconvenience, and later as a clue. Sometimes the particle that looks least domestic turns out to be the one holding the corner of a much larger map. At this point, though, the heavy twin image can take us only so far, because weight alone does not make the tau remarkable. What truly defines its character is what that weight allows nature to do with it. The tau does not simply exist as a heavy version of something familiar. It exists on the edge of immediate transformation. Its mass gives it options, and nature takes those options almost at once. That's where the story becomes even more interesting, because once the tau appears, the clock on its existence is already almost out, and what follows is less a life than a remarkably brief argument with stability. That is where the tau stops feeling merely excessive and starts feeling fragile. Up to this point, we have been talking about it as a heavy twin of the electron, a familiar kind of particle wearing far too much weight. But the real personality of the tau does not lie in its mass alone. It lies in what that mass allows nature to do to it almost immediately. The tau is not built for permanence. It is not one of those patient particles that settles into matter and keeps quiet for billions of years. It is born in energetic circumstances, appears for an absurdly short moment, and then breaks apart into light particles before any detector has the courtesy to greet it properly. In modern experiments, physicists do not usually see a tau as a clean, stable track gliding through an instrument. They see its aftermath. They see the products of its disappearance and work backward from the debris, rather like arriving at a dinner party only to find the loudest guest has already left, but the broken glass, moved chairs, and strong opinions are still in the room. That is not poetic exaggeration. The tau really does have such a short lifetime that it decays before reaching detectors like Atlas, and the way it decays is central to why it is both difficult to study and scientifically valuable. It helps to be careful with the word lifetime here, because it can make the whole business sound more personal and leisurely than it really is. A tau does not carry a tiny wristwatch. It is not born, glances around, checks the weather, and decides that its shift is over. In particle physics, lifetime means something statistical. If you produce a large number of identical taus, they will not all decay at the exact same instant, but they will follow a predictable pattern. Some vanish a little sooner, some a little later, yet the overall average is astonishingly brief. Brief enough that from a human point of view, the tau barely enters existence before it has already become something else. That is the point worth lingering over. The tau is real, but its reality is inseparable from transformation. It does not inhabit the world as an enduring object. It passes through it as a transition. If the electron feels like a stable noun in the sentence of matter, the tau feels more like a verb. The reason for this is not that the tau is somehow defective. It is not a broken electron or an unstable version that failed quality control in the cosmic factory. The tau decays because once you give a charged lepton that much mass, nature suddenly has options. The electron is the lightest charged lepton, which means there is nowhere lower for it to go while still preserving the relevant bookkeeping of charge and the other quantum rules that particle physics takes very seriously. The tau is in a very different position. It is heavy enough to turn into lighter particles while still satisfying those rules, and the weak interaction is more than happy to arrange the paperwork. So the tau does not linger. It sheds mass by becoming combinations of lighter things, usually involving a tau neutrino, and then either lighter leptons or hadrons. The result is a particle that is not merely capable of decaying, but practically eager to do so, as though stability were a lifestyle choice it considered beneath it. This is also what makes the tau distinct from the electron in a deeper way than the simple phrase heavier cousin can capture. The electron is woven into atoms because it can stay put. It orbits nuclei, participates in chemistry, carries electric current through wires, and generally behaves like a permanent employee of the visible universe. The tau cannot do any of that. Give the tau the same electric charge as the electron, give it a formal seat in the same lepton family, even give it broadly similar interactions, and still it does not become a second electron in any meaningful everyday sense. Its mass has changed the entire practical meaning of the particle. This is one of the most important habits in physics, learning when similarity is deep and when it is deceptive. The tau is similar enough to the electron to tempt the comparison, but different enough to make that comparison dangerous if held too tightly. It is not an alternate building block for ordinary matter. It is a fleeting high-energy possibility, a charged lepton that enters the scene only to turn into lighter matter almost at once. Once you accept that, the decays themselves become the whole story. A tau can decay in more than one way, and this branching variety is part of what makes it so useful. In roughly one set of cases, it decays into lighter leptons, producing either an electron or a muon along with neutrinos. In the remaining cases, which are the majority, it decays into hadrons and a tau neutrino. This is a very important detail because it means the tau is the only lepton heavy enough to decay into hadrons at all. That one fact gives it a special status. Electrons do not do this. Muons do not do this. The tau sits at a threshold where the lepton family suddenly overlaps with the hadronic world, and that makes it experimentally rich and theoretically interesting. It is a charged lepton, with one foot still in the familiar lepton category, and the other already kicking open a door into a messier room full of pions and other strongly interacting fragments. In broad terms, about 1/3 of taus decay into electrons or muons, while about 2/3 decay hadronically, and those hadronic decays are notoriously difficult to distinguish from ordinary jets of particles produced in collisions. This is where the tau becomes a detective problem rather than a sighting. If a particle decays before it reaches the main body of a detector, how do you know it was there? The answer is that you do not look for the tau directly in the same way you would look for a long-lived charged particle leaving a neat continuous trail. You look for its children. You look for a very particular pattern of outgoing particles, missing energy carried off by neutrinos, and a geometry that makes sense only if a tau was briefly present at the start of the chain. Physicists become experts in this kind of inference. They know that genuine hadronic tau decays tend to produce a relatively small number of charged particles in a narrow region, unlike the broader and busier jets made by quarks and gluons. They know that leptonic tau decays hide neutrinos, which means some of the energy goes missing in a very characteristic way. The challenge is that collisions at places like the Large Hadron Collider are full of lookalikes. Nature does not line up politely and present one clean tau per event under good lighting. It throws out backgrounds, imitations, near misses, and entire avalanches of particles that resemble one another just enough to make careers difficult. That is why tau reconstruction is a whole craft. The tau is not observed as a stable presence but reconstructed as a likely story. There is something almost philosophically satisfying about that, because it means the tau embodies one of the central truths of modern particle physics. Reality at very small scales is often not about enduring things but about permitted changes. We begin our scientific education by imagining matter as little pieces. Later we learn that the more faithful picture is full of interactions, transitions, decays, and probabilities. The tau fits that mature picture beautifully. It is not interesting despite its instability. It is interesting through its instability. The way it vanishes is precisely the way it reveals itself. Every decay channel is a clue to the structure of the weak interaction, to the universality of lepton behavior, to the possibility that heavy leptons may expose tiny deviations from the standard model more clearly than lighter ones do. In other words, the tau does not simply disappear and leave us empty-handed. It disappears in structured ways, and those structures can be measured. That is a very physics kind of consolation. The suspect may keep fleeing the room, but he does insist on dropping useful paperwork on the way out. This short life also does something else for the imagination. It reminds us that not every fundamental particle is meant to furnish the visible world. Some are there as brief permissions written into the laws of nature. The tau tells us that the universe allows a heavy charged lepton to exist, but only under energetic conditions and only momentarily. That distinction matters. There is a tendency, especially when first learning particle physics, to think that if something is fundamental it ought to be common, or stable, or somehow central to everyday reality. The tau corrects that assumption. Fundamental does not mean familiar. It does not mean useful to chemistry. It does not mean likely to appear in your breakfast. It means the particle belongs to the underlying rulebook, whether or not the ordinary world takes advantage of it for very long. In that sense, the tau is less like a brick in the walls of the universe, and more like a rare note in the score, one that sounds only when the orchestra is playing at full force. And yet, for all its brevity, the tau is not minor. Heavy particles have a habit of mattering out of proportion to their lifespan. Because the tau is the heaviest lepton, it can test parts of the theory that lighter leptons cannot access in the same way. It can reveal whether the underlying interactions really treat the three lepton generations equally once mass effects are properly accounted for. It can appear in the decays of heavier particles such as the Higgs boson. it can become a sensitive place to look for hints that the standard model is ever so slightly incomplete. This is one of those moments where science becomes wonderfully unfair to intuition. The particle that vanishes almost at once ends up carrying a surprising amount of conceptual weight. The one that refuses to stay still long enough for comfort becomes one of the best ways to check whether our deepest theories are leaning in the wrong direction. So the tau is born to vanish, yes, but not to be irrelevant. If anything, its unreliability is part of what makes it such an effective witness. There's also a nice contrast here with the way we talk about death in ordinary language. In daily life, when something vanishes, that often sounds like an ending. In particle physics, decay is not really an ending at all. It is more like translation. The tau becomes other particles according to very strict rules. Charge is conserved, momentum is conserved, energy is conserved. The deeper accounting never slips. The drama is all on the surface. One form gives way to several others, and what looked like a disappearance is really a redistribution. This is worth sitting with because it captures the underlying mood of high-energy physics rather well. The universe is not a place where tiny objects simply blink out in defiance of reason. It is a place where unstable arrangements flow into stabler ones, where mass opens channels, where possibility narrows into outcomes. The tau is temporary, but the laws governing its temporary nature are not chaotic. They are precise enough that whole experiments can be built around them. That precision, though, does not make the tau feel any less dramatic. There is still something wonderfully impatient about a particle that arrives carrying so much mass and then immediately resolves not to keep it. You can almost understand why experimental physicists speak of taus with a mixture of respect and weariness. To work with them is to chase something that never stands still. It is to infer a hidden parent from visible fragments and invisible neutrinos. It is to separate genuine tau signatures from a crowd of pretenders. It is to look at a collision and ask whether this narrow spray of hadrons, or this electron with missing energy, or this muon accompanied by the right kinematic pattern, might be the footprint of a particle that was gone before the apparatus really had a chance to register its presence. That is difficult work, but it is also exactly the kind of work that modern physics has become very good at. The field has learned again and again that some of the most important truths arrive indirectly. So when we say the tau is a particle born to vanish, we are not making a literary flourish. We're describing its central physical character. Its mass gives it many allowed exits. The weak interaction ushers it through one of them almost immediately. Some of those exits lead to lighter leptons, most lead to hadrons and a tau neutrino. All of them make the tau hard to catch and impossible to treat as a calm component of ordinary matter. The tau is not furniture. It is an event. It is not a stable resident of the world you touch every day. It is a flash of permission in the laws of nature, one that leaves just enough evidence behind for skilled people to reconstruct its brief existence. And that is precisely why the next part of the story matters so much, because before the tau could become a tool for testing the universe, it first had to be found at all, which is no small task when your quarry is already gone by the time you know to look for it. Finding the tau was not one of those tidy scientific moments where someone looks in the correct place, sees the expected thing, and calmly writes a triumphant paper before lunch. It was messier than that, and much more human. The search began with a feeling that something was missing from the story of the charged leptons. By the early 1970s, physicists already knew the electron and the muon, and Martin Pearl had become interested in the possibility that there might be another charged lepton hiding at higher energies. As he later explained, he had originally hoped to uncover the connection between the electron and the muon, and when that connection did not reveal itself, he decided to look for an additional heavier lepton instead. That detail matters, because the tau was not discovered by accident in the purest sense. It was not a random gift dropped on physics by a distracted universe. It was found by people who had begun to suspect that the lepton family might not be finished yet, even if they did not know what form the next member would take. Pearl and his collaborators were searching for a possibility, not a certainty, and that is often how major discoveries begin. Not with confidence exactly, but with a stubborn willingness to ask whether nature has one more trick in reserve. The machine that made this possible was called SPEAR, an electron-positron storage ring installed at the Stanford Linear Accelerator Center in 1973. It mattered because it gave physicists a cleaner way to hunt for new leptons than many earlier experiments had offered. In earlier searches, including work Pearl had done in the 1960s, no new charged leptons had been found. But SPEAR opened a new energy range and a new style of experiment. Instead of smashing particles into a fixed target and trying to decipher a more cluttered aftermath, researchers could collide electrons and positrons head-on and look for the creation of new particle pairs in a setting that was easier to interpret. That sounds very neat when said quickly. In practice, it meant years of hard experimental work, careful detector design, and the kind of patience that only particle physicists and people untangling holiday lights seem able to sustain for long periods. The key point is that SPEAR gave Pearl and his team a chance to search where earlier machines could not. Other groups had looked for new charged leptons before, including teams at the Adone facility in Italy, but those efforts had not reached the energy needed to produce a tau pair, if the tau was as heavy as it turned out to be. So the story of the tau begins not only with curiosity, but with technology finally catching up to curiosity enough to let the universe answer back. The first hints did not announce themselves with anything so courteous as a complete tau neatly labelled in a detector. What the team began to see in 1974 and reported in 1975 were strange events that did not fit comfortably into the expected patterns. In a number of collisions, they found an electron on one side and a muon on the other, carrying opposite charges. But the event as a whole did not balance in the simple way ordinary two-particle production should have. The visible particles were not arranged back-to-back in the clean fashion one would expect if nothing else had been produced. Something was missing, or rather several somethings were missing. The data suggested that invisible particles had carried away a substantial amount of energy and momentum. That was the awkward clue. If all you had were the visible particles, the event looked wrong. But if invisible neutrinos had also been created, the bookkeeping could be made to work again. That led Pearl and his collaborators to a bold interpretation. Perhaps these odd events were not direct electron muon production at all, but the decay products of a new pair of heavy unstable particles, each of which had been produced in the collision and then decayed almost immediately. One became an electron and invisible neutrinos, the other became a muon and invisible neutrinos. In other words, they were not looking straight at the new particle. They were looking at a scene after it had already vanished. The Nobel material describes the first sign as the observation of 24 such anomalous events, which is exactly the sort of number that sounds both thrilling and deeply annoying, because it is enough to raise hope and not nearly enough to silence doubt. That doubt was important. Particle physics has a long and colourful history of people getting excited too early, and the field has developed a healthy suspicion of its own enthusiasm. A few anomalous events are not the same thing as a discovery. Detectors can mislead. Background processes can imitate new physics. Statistical fluctuations can create brief mirages. So even after the 1975 paper, the case was not closed. In fact, one of the most interesting parts of the tau story is that the discovery unfolded over several years. Nobel Prize sources note that the first results were reported in 1975, but that it took more time before Pearl and his collaborators, along with other groups, could convincingly show through detailed analysis that these anomalous lepton pairs really were evidence of a new heavy lepton. That slower pace is worth remembering, because science often looks instantaneous in hindsight. We compress discovery into a date, a headline, a prize citation, a neat line in a textbook. But the real process is usually stretched out and rather untidy. First, there is the strange signal, then the arguments, then the cross-checks, then more data, then the gradual shift from maybe to probably, and from probably to yes, this really is something new. By the end of that process, the heavy lepton hypothesis had stood up to repeated testing, and the new particle became accepted as the third charged lepton. The name tau was chosen from a word meaning third, which feels almost modest given how much trouble the thing would cause for physicists afterward. There is something wonderfully understated about that. Not a grand title announcing cosmic revolution, just a quiet nod to its place in the sequence, as though the universe had simply opened the drawer and admitted there was in fact another one. What made the evidence persuasive was not a single dramatic flash, but the way many pieces began to fit together. If the new particle were a heavy lepton, then it should be produced in pairs in electron-positron collisions once the energy is high enough. It should decay quickly. It should produce final states involving lighter leptons and neutrinos, or other combinations consistent with the weak interaction. The missing energy should not be random nonsense but a natural consequence of neutrinos slipping out of the detector unseen. The rates should behave in a consistent way as the collision energy changes. The events should not be explainable as a known process wearing a false moustache. Over time, that pattern hardened. The anomalous events were not just odd, they were coherent. They behaved like the fingerprints of a new unstable charged lepton. That is one of the beautiful features of experimental physics at its best. A discovery is rarely one dramatic shout. It is a chorus of small agreements. This track points here, that imbalance points there. This production threshold opens when it should. That background estimate fails to explain the excess. Soon the story is no longer being held together by optimism. It is being held together by evidence. When the Nobel Prize later recognized Martin Perl in 1995 for the discovery of the tau lepton, it was acknowledging not just a clever hunch, but a long chain of experimental reasoning that had turned a puzzling set of events into one of the central facts of particle physics. There is also a larger historical backdrop that makes the discovery feel even more striking. The tau did not just add one more particle to an already busy shelf. Nobel sources describe it as the first sign of a third family of elementary constituents of matter. That is a much bigger statement than it might appear at first. Before the tau, particle physicists already had the first family well established, and the second family was becoming firmer through work on the charm quark and the muon sector. But the tau suggested that nature had not stopped there. The family portrait had another role. Later the bottom quark would be found, and still later the top quark, completing that third family in the standard model picture. Seen from that angle, the discovery of the tau was not merely the discovery of a heavy lepton, it was the opening crack in a much larger wall. It told physicists that the structure of matter came in 3 generations, not 2, and that what looked at first like an extra particle was actually the first visible member of a deeper pattern. This is one reason the discovery caused such surprise. A new particle is exciting enough. A new family is a different level of inconvenience entirely. It is the kind of result that does not just add a fact, it rearranges the filing system. And yet it is very much in character that the tau arrived in the most indirect way possible. A particle built to vanish was never going to stroll politely into the detector and pose for a portrait. It had to be inferred from decay products and missing energy, from imbalance that became meaningful only when interpreted with care. That is part of why the discovery story feels so appropriate for the tau itself. Everything about this particle resists simplicity. It looks familiar, but is far heavier than it ought to be. It belongs in a clean family pattern, but makes that pattern harder to explain. It is real beyond question, and yet can only be known through traces because it decays too fast to remain visible for long. Even its discovery followed that same character. Not a straightforward appearance, but a brief disturbance in the data, a whisper of invisible companions, an argument made from what was missing as much as from what was present. There is something almost wonderfully perverse about that. The particle that complicates the standard model also chose to complicate its own introduction. Martin Perl later said, with a kind of dry honesty that one comes to appreciate in physicists, that his discovery may have raised more questions than it answered. That is a remarkable sentence, and probably one of the best ways to describe the tau. Discoveries in science are often imagined as doors closing, as uncertainty being replaced by knowledge. Sometimes they are, but some discoveries are more like new corridors appearing in the house. You open one door and find 5 more beyond it. The tau was exactly that kind of result. Once it was accepted, physicists still had to ask what connected the electron, the muon, and the tau. Why 3 charged leptons? Why these masses? Why this family structure? What law fixed the pattern? Those questions remain stubborn even now, so in a sense the tau was found twice. First it was found experimentally, in the collisions at Spear and the careful analysis that followed. Then it was found conceptually, as a problem, as a demand, as a feature of nature that would not go away and would not fully explain itself. That second discovery is still ongoing. We know the tau exists. We know a great deal about how it behaves, but the larger reason it belongs in the universe at all still feels tantalizingly unfinished. Perhaps the loveliest part of the story is that it captures what science actually feels like when it is working properly. Not certainty marching in a straight line, but disciplined curiosity living with ambiguity long enough to turn it into knowledge. The people at Spear did not begin by saying there is definitely a 3rd charged lepton, and here is its complete description. They began with odd events, incomplete information, and a detector telling them that something about the collisions did not make the usual kind of sense. From there came hypotheses, tests, more data, more skepticism, and eventually acceptance. It is tempting to smooth that into legend, to make it sound inevitable. It was not inevitable, it was earned. And because it was earned, the tau entered physics not as a rumour or a decorative speculation, but as something measured, argued for, challenged, and finally absorbed into the structure of the standard model. Which leaves us with a curious mood. We admire the discovery because it was so careful. We admire the particle because it is so real, and at the same time the better established the tau became, the stranger the universe looked for containing it. Once the evidence was secure, the awkward question only grew louder. Not did we find it, but why was there something there to find in the first place? That is where the next part of this journey naturally leads, because having watched the tau emerge from the data, we can now turn toward the deeper discomfort it creates. A heavy charged lepton, a 3rd family, a particle whose existence is experimentally solid and conceptually inconvenient, begins to force a larger question about what the standard model does beautifully and what it still does not truly explain. Now we arrive at the uncomfortable part. Up to this point, saying that the tau should not exist may have sounded like a bit of dramatic overstatement, the sort of phrase one uses to keep a scientific story lively, while everyone politely agrees that, well, obviously it does exist because we found it. But there is a serious meaning tucked inside that line, and it is worth taking slowly. Physicists do not mean that the tau violates the standard model merely by turning up. The standard model includes it perfectly well. It has a place in the table, its charge is known, its interactions are known, its decays can be calculated, experiments have measured its properties again and again. So the issue is not that the tau is illegal, the issue is that it feels unjustified. It feels like one of those details a theory accepts without truly explaining, and once you notice that, the whole structure begins to look a little less complete than it first appeared. The simplest way to see the problem is to start with the world we actually live in. Ordinary matter does not need the tau. The atoms around you are built from electrons, up quarks, and down quarks. Those are enough to construct nuclei, atoms, molecules, chemistry, stars, oceans, fingernails, old books, door frames, and all the rest of it. The first generation of matter particles already does the practical work of building a lasting universe. In that sense, the visible world is surprisingly economical. It gets an extraordinary amount done with a very small set of ingredients. And then, once physics has shown you that remarkable economy, it quietly reveals that nature has also included a 2nd and 3rd generation of particles that look suspiciously like repeats. The muon repeats the electron in a heavier form. The tau repeats it again in a heavier still form. The same broad pattern happens for quarks, and that is where the unease begins. If the first generation is enough to build the world, why are the others there at all? That is the strongest meaning of the phrase. The tau should not exist in the sense that nothing in the everyday architecture of matter seems to require it. It is not needed for stable atoms. It is not needed for chemistry. It is not needed for ordinary planetary life. It is not needed for a calm universe made of persistent structures. If you were trying to invent the leanest possible version of known matter, the tau would be one of the first things crossed off the list. And yet nature has not crossed it off. Nature has kept it in the official cast, given it a very large mass, allowed it to appear in energetic processes, and then let it vanish quickly enough that it never becomes part of the visible furniture. This is not a contradiction. It is something more irritating. It is a redundancy that appears to be fundamental. That word redundancy matters, though it must be handled carefully. In science, what looks redundant often turns out not to be redundant at all once the deeper theory is uncovered. There may be a hidden reason the generations come in three. There may be a larger symmetry or structure from which the electron, the muon, and the tau emerge naturally. There may be a mechanism that makes the repetition unavoidable. But if such a mechanism exists, the standard model does not fully hand it to us in a satisfying way. Instead, it presents the families of matter as facts to be accepted. It says, in effect, here are the particles, here are their charges, here are the strengths with which they couple to the Higgs field, here are the masses that result, and here is how they behave. It is astonishingly good at using that information. It is much less good at telling us why that information has the values it does. This is why the tau becomes a symbol of a larger problem known as the flavor problem. Though I will say that phrase only this once because it tends to sound as though physics has wandered into a kitchen and become disappointed with the soup. What scientists mean is the problem of family structure. Why are there several generations of matter particles with the same basic charges and interaction patterns but different masses? Why does the electron have its particular small mass? Why is the muon heavier? Why is the tau heavier still? Why are the quarks spread across such a huge range of masses? Why do the mixing patterns among quarks and neutrinos take the forms they do? The standard model contains these facts, but it does not derive them from a deeper first principle in a way that leaves everyone calm and reassured. So when people say the tau should not exist, part of what they mean is that the theory has not given us a reason to expect such a particle before looking at nature and discovering that nature, inconveniently, has included one. There is a useful contrast here between prediction and accommodation. A theory predicts something when the structure of the theory almost forces it into existence. The positron is a famous example from an earlier era. Certain mathematical features of relativistic quantum theory made room for an antiparticle to the electron, and when the positron was found, it felt like a deep confirmation that the theory was speaking clearly about reality. The tau is a different sort of case. Once the standard model is written with 3 generations, of course the tau belongs there. But the deeper question is why the model has 3 generations to begin with. That is not something the theory explains in a compellingly final way. It is something the theory accommodates. The tau fits beautifully into the completed pattern, but the existence of the pattern itself still feels like an unanswered question. Another way to put it is that the tau is not mysterious because it is messy. It is mysterious because it is neat in the wrong way. If nature had given us 100 totally unrelated particles with random charges and random interactions, that would be chaos. We would complain, but at least we would know what the complaint was. The tau is more subtle than that. It looks organized. It looks like part of a rule. It resembles the electron too closely to be a random accident. It sits in a clear family structure, and yet the reason for the repetition remains obscure. So the tau does not break the order of the standard model. It draws attention to the fact that the order may be more like a pattern we have catalogued than one we have fully understood. Mass makes this worse. If the muon and tau were merely a little heavier than the electron, perhaps one could imagine them as mild variants with only minor consequences. But the actual mass differences are enormous. The tau is not politely above the electron. It is vastly above it. That means the resemblance in charge and interaction looks even more peculiar. It is as though nature has copied the template of the electron and then turned one setting wildly upward, without leaving a note explaining why. The standard model can live with that. It assigns different coupling strengths to the Higgs field for different particles and outcome different masses, but that only moves the question one step back. Why those coupling strengths? Why that pattern? Why the tiny value for the electron and the much larger one for the tau? Saying the theory allows it is not the same as saying the theory explains it. This is where people sometimes reach for the word naturalness, which has caused almost as much trouble in modern theory as it has insight, because the universe is under no obligation to satisfy human notions of what feels tidy. Still, the intuition behind the word is not foolish. When a theory contains numbers or structures that seem oddly placed, scientists start wondering whether some hidden principle is missing. The tau contributes to that feeling. It belongs to a family of particles that seem duplicated without obvious purpose. Its mass is much larger than the electrons without a simple explanatory rule. Its existence is not demanded by the visible world. It feels like a clue that some more fundamental layer of theory has not yet been reached. In that sense, saying it should not exist is a way of saying it should not exist if the visible world and the current explanatory tools were the whole story. Since it does exist, perhaps they are not. There is also the question of why there are exactly 3 generations and not 1, or 4, or 17. This is one of those scientific facts that becomes stranger the longer you sit with it. 1 generation would make a certain kind of stark sense. It would be austere and economical. 2 generations would already invite questions, but perhaps you could imagine some balancing act or hidden pairing. 3 generations is enough to feel intentional, but not enough to explain itself. It is the number at which regularity becomes impossible to ignore, and meaning remains frustratingly out of reach. The tau, as the third charged lepton, sits exactly at that point of discomfort. It is not just an extra particle, it is the final charged lepton in a repeated sequence, and repeated sequences in nature usually make scientists suspect there is a deeper grammar underneath. If there is, we have not read it cleanly yet. One might ask whether this is simply a matter of human taste, whether physicists are being fussy because nature declined to write the universe in the most elegant shorthand. There is some truth in that, and science has often had to learn humility when the universe turned out to be less aesthetically obedient than hoped. But the tau is not merely an offence against tidiness. Its existence connects to other unresolved questions in a very practical way. The pattern of masses and generations affects how particles decay, how the weak interaction mixes flavours, how neutrinos oscillate, how early universe processes may have unfolded, and how possible new physics beyond the standard model might reveal itself. So the discomfort is not just philosophical. It points toward real gaps in our understanding. Consider the first generation again. It is enough to build stable matter. That is a powerful clue. It suggests that the second and third generations are not there because atoms demanded them. They are there because the underlying laws do. But those laws, in the form we currently write them, do not tell us why in a fully satisfying way. This leaves the tau in a peculiar position. It is unnecessary from the point of view of ordinary material construction, yet necessary from the point of view of accurately describing nature as experiments reveal it. That tension is exactly what makes it feel like an unresolved message. The universe is saying, yes, your world can be built from simpler ingredients, but the laws beneath that world are not so minimal after all. There is a wonderfully annoying possibility hidden in all this, which is that the tau may exist not because it serves some local practical purpose, but because it is part of a deeper architecture that only becomes visible when one steps back far enough. This has happened before in science. Structures that seem wasteful or accidental at one level turn out to be inevitable consequences of a broader framework at another. If some larger theory unifies quarks and leptons, or explains the pattern of families through symmetries that only show themselves at very high energies, then the tau might eventually look perfectly natural. But until such a theory is established, the particle retains its air of awkwardness. It is like having a key to a room you have not found. The key is real. It clearly belongs to something. But until the door appears, the object feels misplaced. The tau also sharpens a more general lesson about successful theories. A theory can be astonishingly predictive and still leave deep questions unanswered. This is not a flaw unique to particle physics. Newtonian gravity described planetary motion beautifully without revealing the deeper geometric nature of gravitation that would come later. Early quantum theory accounted for many atomic phenomena before the full structure of quantum mechanics and quantum field theory had properly matured. In that tradition, the Standard Model may be a magnificent intermediate truth. It may describe the particles and forces we observe with extraordinary precision while still sitting inside a larger theoretical framework that explains why its ingredients are what they are. The tau is one of the reasons that suspicion persists. Its existence feels like a fact the current theory handles well but does not illuminate deeply enough. There is another more psychological reason the tau feels like it should not exist. It offends the quiet intuition that heavy unstable particles ought to have some obvious job to justify their inconvenience. The top quark, for example, is also extraordinarily heavy, but quarks already live in a rougher neighbourhood. They participate in the strong interaction. They come in confined combinations. They inhabit a sector of the theory that is complicated almost by default. The tau, by contrast, belongs to the lepton family, where the comparison with the electron is so direct that the repetition becomes impossible to ignore. It is the cleanest kind of duplication. That makes it harder to dismiss as just one more strange detail in an already crowded zoo. The tau is not hidden in a murky corner. It is sitting right next to the electron in the conceptual portrait, forcing the eye to compare them. And when you compare them, the question becomes almost embarrassingly plain. Why is one stable and indispensable, while the other is heavy, fleeting, and apparently unnecessary for the visible world? Why does nature need both? Or perhaps that is already the wrong word. Need may be too domestic a concept for particle physics. The universe does not need anything in the way a carpenter needs a hammer. Still, we search for underlying economy because economy has often been a guide to truth. When that economy seems absent, or at least hidden, we take notice. The tau is one of those absences. It does not make the Standard Model fail. It makes the Standard Model feel provisional. This is also where one must be fair to the particle itself. Saying the tau should not exist is not a dismissal. It is almost a compliment. It means the tau is so revealing that it exposes the limits of our current explanation. It means the particle is important enough to be a problem. Many particles simply fit. The tau fits and still disturbs. It is that rare scientific object which becomes more interesting the more securely it is established. If it were uncertain, one could shrug and wait. If it were fully explained, one could admire it and move on. But the tau inhabits the more uncomfortable middle ground. It is undeniable and still conceptually provocative. Once you begin to see it that way, the phrase takes on a more precise meaning. The tau should not exist if all we ask of physics is a minimal account of the visible world. It should not exist if repetition without explanation is taken as a sign that something has gone wrong with our expectations. It should not exist if a fully satisfying theory ought to tell us why matter comes in these families and why the masses take the values they do. Yet it does exist, and because it does, we are pushed toward a more ambitious view. Perhaps the visible world is only the calm surface of a deeper structure. Perhaps the family pattern of particles is a trace of hidden symmetries or broken ones. Perhaps the tau is not an absurd extra, but a witness to laws we have not fully uncovered. That is why the discomfort around the tau is productive rather than despairing. It does not merely tell us that something is odd. It tells us where to press. It tells us to examine the universality of lepton interactions. It tells us to compare electrons, muons and taus with unusual care. It tells us to study how the heavy leptons are produced and how they decay. It tells us to ask whether the standard model is treating all 3 generations exactly as it should, or whether tiny discrepancies are beginning to appear. In other words, the tau should not exist, and since it does, the reasonable response is not outrage, but investigation. And that leads naturally to the next layer of the story, because the tau does something very peculiar. It manages to feel as though it breaks the spirit of simplicity without breaking the formal rules of the theory. It is rebellious in a very disciplined way. It does not smash the laws of particle physics. It obeys them with almost irritating precision, while still leaving us with the sense that the deeper logic has not been fully told. That is a subtle distinction, but it matters, because the tau does not announce new physics by being openly impossible. It does something more interesting than that. It behaves like a proper citizen of the standard model, and still makes the standard model feel unfinished. There is a difference between a particle breaking a rule and a particle making a rule feel embarrassingly incomplete. The tau belongs to the second category. It does not violate the standard model by existing. In fact, the standard model has a very definite place for it. It is a charged lepton, it comes with its own neutrino, and it participates in the electromagnetic and weak interactions exactly where the theory says it should. The trouble is more subtle than outright disobedience. The tau behaves like a proper citizen of the theory, while still making the theory look as though it is withholding part of the explanation. That is why it seems to break something without actually breaking it. It breaks our expectation that a fundamental theory ought to be economical, transparent and eager to explain why one charged lepton was not enough. But in formal terms, the tau sits inside the rules rather than outside them. Recent CERN and Atlas summaries still describe it that way, as the heavier short-lived lepton, fully part of the standard model, yet special because its mass and behaviour make it one of the most sensitive places to look for anything beyond that model. One rule it appears to break is sameness. If you look only at the lepton family from a distance, electrons, muons and taus are supposed to be treated alike by the weak interaction. That principle is called lepton flavor universality. CERN describes it plainly. As far as physicists know, the only difference between the electron, muon and tau is their mass, and the weak force should couple to all 3 with equal strength, apart from very small corrections caused by those mass differences. In other words, the deep rule says the 3 flavors are equals in the eyes of the weak interaction. Yet the tau does not feel equal in any ordinary sense. It is vastly heavier, far less stable, much harder to reconstruct, and much more dramatic in the way it enters and leaves an experiment. So to intuition, it looks as though universality has somehow failed. But the actual measurements do not support that suspicion. Atlas reported in 2024 that its most precise single experiment test of electron and muon decays of the W boson gave a ratio of 0.9995 with an uncertainty of 0.0045, fully compatible with equality, and the same CERN summary emphasizes that universality remains intact. The tau makes the family look unequal, but the rule it belongs to still survives. That is what makes the tau so sly. It does not break universality at the level where the standard model is actually tested. It breaks universality emotionally. It looks unfair. It looks like the same particle template has been given wildly different weights, lifetimes and practical roles. And in a certain sense that is true. Atlas put it rather nicely in a public briefing when it noted that only the Higgs interaction really knows the difference between the electron, the muon and the tau, and that it treats them very differently, especially the tau, for reasons that are not understood. That sentence captures the whole discomfort. The weak force says the flavors are equals. The Higgs-related mass pattern says they are absolutely not equals in any everyday sense, so the tau seems to break a clean symmetry, while actually leaving the symmetry of the weak interaction untouched. The rule still stands, but it stands next to another fact that makes it look oddly incomplete. We can say with confidence that the tau is treated like the other charged leptons by the weak force, and we can also say with equal confidence that nature has burdened it with a mass that makes it behave like a very different creature in practice. Those two truths sit together quite legally, and that legal coexistence is precisely what feels suspicious. Another rule the tau seems to break is the tidy division between the durable pieces of matter and the fleeting ones. The electron is the quiet professional of the family. It remains stable and useful. It helps build atoms, chemistry, currents, and all the material arrangements that make ordinary life possible. The tau, by contrast, shows up and immediately starts falling apart. That can look like a kind of failure, as though nature made a charged lepton and then neglected to make it last. But again, nothing unlawful is happening. The tau is heavy enough that the weak interaction can convert it into lighter particles while preserving charge, energy, momentum, and the rest of the sacred bookkeeping. The standard model expects this. In fact, the measured branching fractions fit together in a strikingly orderly way. The particle data group gives the tau branching fraction to a muon and neutrinos as about 0.1739, to an electron and neutrinos as about 0.1782, and the global fit of exclusive decay modes is consistent with unitarity, meaning the full set of allowed decays adds up as it should. So the tau does not break the rule of conservation at all. It only breaks the gentler human expectation that something so official ought to have the manners to stay put. This leads to a further kind of apparent rebellion. The tau feels like it breaks the clean identity of a lepton because it can decay into hadrons. For many people first meeting the particle world, leptons and hadrons seem like separate neighbourhoods with a respectable hedge between them. Electrons belong over here. Pions and kaons belong over there. But the tau is heavy enough that its weak decay can produce hadronic final states, and that makes it the only lepton for which this becomes a major feature of its behaviour. That sounds almost scandalous at first, like a violinist suddenly deciding to leave the orchestra and become a roofer. Yet the rule has not been broken. The tau itself remains a lepton. The decay happens through the weak interaction, which can produce quark pairs that then form hadrons. In other words, the hedge was never absolute. It was only that lighter charged leptons never had enough mass to make the crossing in this dramatic way. The measured branching fractions make that clear. Since the purely leptonic channels account for a little over 1/3 of tau decays, the rest are predominantly hadronic, which is exactly why experiments spend so much effort separating genuine tau decays from ordinary hadronic jets. The tau appears to step out of character, but really it is just the first lepton heavy enough to make full use of the permitted exits. It also seems to break the rule that a particle ought to be observed if it is to be trusted. This is one of the most modern and slightly unnerving features of high-energy physics. We are often not looking at things in the ordinary sense. We are reconstructing them from consequences. The tau is a perfect example because, as Atlas notes, taus are the trickiest leptons to measure since they do not live long enough to interact with detectors in the direct way stable charge particles do. Physicists infer their presence from the particles produced when they decay, while trying to remove the fakes that mimic tau signatures, so the tau feels like it violates a common-sense rule of evidence. You never really catch it standing there. You catch what remains after it has already gone. But this too is not a break in logic. It is a reminder that the scientific meaning of seeing is broader than everyday sight. If the decay products, missing energy patterns, production rates, and detector signatures match the same underlying story again and again, then the particle is as real as any object in the field can be. The tau does not break evidence. It enlarges what evidence must mean when the objects under study live on vanishing timescales. There is another sense in which the tau appears to break a rule, and this one cuts closer to theory. It seems to violate simplicity. The first generation of matter is enough to build ordinary atoms and the stable world around us. That gives a strong impression that one charged lepton should have been sufficient. Then nature adds the muon, which already feels a little unnecessary, and then the tau, which feels even more unnecessary, especially because it is heavier than both, and decays almost immediately. But the standard model does not contain a commandment that says the universe must be minimal. That commandment exists only in our taste. What the model does say is that if particles of these generations exist, they should interact in specific ways, decay in specific ways, and contribute to experiments in measurable patterns. The Tau follows those instructions extremely well, so once again it breaks a rule we were hoping for rather than a rule the theory actually imposes. This is a useful distinction. Physics is full of moments where the universe disappoints our preference for elegance while remaining perfectly lawful. The Tau is a master of that kind of disappointment. It makes the deep theory feel incomplete without giving us the satisfaction of an outright contradiction. In fact, recent Tau measurements make this even more pointed. If the Tau were truly breaking the standard model, one might expect its production or decay patterns to be visibly drifting away from what the theory predicts. But that is not what the latest high-energy measurements are finding. Atlas reported in 2025 that it had compared measured high-energy tau-pair production directly with standard model predictions, and found that those predictions describe the data very well. That does not mean the story is finished. It means the Tau keeps obeying the written rules, while still tempting physicists to suspect there may be unwritten ones behind them. It is a very particular sort of frustration. A badly behaved particle would be easier, in a sense. You would point to the disagreement and say there, that is where the new physics lives. The Tau is harder because it keeps acting like a disciplined witness. It cooperates with the established theory just enough to deny us a simple revolution, while remaining special enough in its mass and family position to keep people wondering whether a deeper layer of structure has not yet come into view. This is also why the Tau sits so naturally in searches for new physics, even when those searches come up empty. The same Atlas briefing explains that many possible extensions of the standard model give a special role to third-generation particles, and the Tau in particular, precisely because the Higgs boson couples much more strongly to the Tau than to the electron or muon. If a new particle mixes with the Higgs boson, it will often prefer to decay into the heaviest particles it can reach, which frequently means taus. So the Tau seems to break the rule that a particle should justify its presence in the visible world by being useful there. It is not useful to chemistry or atoms, but it may be useful to the deeper architecture of particle physics. It may be the kind of object that looks redundant only from the narrow point of view of household matter. In the broader language of high-energy theory, it can become one of the most revealing channels through which hidden structure might eventually announce itself. That possibility has not yet been confirmed, but it explains why the Tau remains a place of such intense attention. There is a more formal version of this same theme in the way the Tau handles decay bookkeeping. Because it has many possible decay channels, one might imagine its behaviour becoming messy enough to undermine the neat accounting of the theory. Yet the global fits do the opposite. The particle data group notes that the full fit of exclusive Tau decay modes is consistent with unitarity, with the sum behaving as expected. That is a beautifully stern result. It means the Tau, despite its many ways of falling apart, is not leaking probability or inventing mysterious disappearances behind the curtain. The branching pattern is complicated, yes, but the complication still sits within a closed and disciplined mathematical framework. So even the particle most likely to give the impression of chaos turns out to be obedient when the accounts are checked. It seems to break order by having too many exits, too many signatures, too much practical awkwardness. Then you do the actual fit, and the numbers line up. There is something almost comically proper about that. The Tau barges into the room looking like a source of disorder, and then leaves behind bookkeeping that balances. All of this helps explain why the Tau has such a peculiar personality in physics. A genuinely forbidden particle would be easier to narrate, so would a fully ordinary one. The Tau is neither. It is lawful and troublesome at the same time. It does not violate the deep conservation laws. It does not overthrow lepton flavor universality in the measurements that currently test it. It does not ruin the internal counting of its own decays. It does not refuse to fit into the standard model table. but it does create the sense that something important remains unexplained. Why 3 generations? Why such a dramatic mass hierarchy? Why should the Higgs-related mass pattern distinguish so brutally between particles that the weak interaction otherwise treats alike? Those are not complaints about broken rules in the formal sense. They're complaints about a theory that may be descriptive in places where we still long for explanation. The Tao keeps pointing at that distinction. It is the particle that obeys everything we can currently write down, while quietly asking whether what we have written down is the final draft. And perhaps that is the most interesting rule it breaks without breaking. It breaks the comforting idea that if a theory works brilliantly, the deeper reasons must already be in hand. The Standard Model is one of the most successful theories in the history of science, and the Tao behaves exactly as one of its particles should. Yet the Tao also makes it clear that predictive success is not the same thing as conceptual closure. The theory tells us how the Tao behaves. It does not fully tell us why nature wanted such a particle in the first place. So the Tao lives in that narrow and fascinating region where a particle can be completely legitimate and still feel like evidence against complacency. It obeys the rules, keeps the books balanced, respects universality where universality is supposed to hold, and still leaves us with the very strong impression that the universe has more background to offer than it has so far admitted. Which is why, once we have watched the Tao follow every formal instruction with almost irritating discipline, the next thing to notice is how brief that disciplined existence actually is. Because whatever else the Tao may be, it lives less like a resident of the world than like a mayfly in a storm of energy. The Tao does not really have what most of us would call a life. It has a legal right to existence, certainly. It has a mass, a charge, a place in the Standard Model, and a long record of experimental study. But if you try to imagine it as a stable, tiny resident of the universe, something that arrives and then calmly remains itself for a while, the picture fails almost immediately. The Tao is too brief for that. According to the particle data group, its mean lifetime is about 290.3 femtoseconds, which is roughly 2.9 times 10 to the minus 13 seconds. Atlas describes it more bluntly. The Tao does not live long enough to interact with the detector as a stable charged particle, so physicists have to reconstruct its presence from what it leaves behind. That is a very small sentence with a very large implication. The Tao is not a particle you meet in the ordinary way. It is a particle you infer from the traces of its departure. That extreme brevity can be hard to feel properly, because human intuition is not built for timescales like this. A second already feels small when one is talking about nerve signals, camera shutters, or the pause before someone replies to a text message. A femtosecond is smaller by an absurd margin, and the Tao gets only a few hundred of them on average. At rest, the same particle data group listing corresponds to a characteristic travel distance of about 87 micrometers, which is not even enough to cross the thickness of a human hair. In collider conditions where the Tao is often produced moving at a significant fraction of the speed of light, that tiny lifespan stretches into something experimentally useful, but only just. Atlas notes that a Tao carrying about 40 giga-electron volts of momentum can fly around 2 mm before it decays. 2 mm is enough to matter to a precision detector, enough to shift the apparent origin of its decay products, enough to let careful physicists separate a prompt particle from one born of a Tao decay. But it is still a fleeting existence. The Tao is not a traveller in the way a muon can be in a detector. It is more like a very brief detour in the geometry of a collision. This is why the mayfly comparison is not really exaggeration. A mayfly in ordinary life is famous not because it fails to exist, but because it compresses so much of its visible presence into a brief interval. The Tao does something similar on a scale so extreme that the word brief begins to feel almost decorative. It is born in a violent event, usually where enough energy has been concentrated to produce something as heavy as a Tao in the first place, and then nature starts taking it apart almost at once. That is not an accident and it's not a flaw. And It is the direct consequence of the tau being heavy enough for many lighter final states to be available through the weak interaction. The standard model does not regard this as a scandal, it regards it as business as usual. The tau is the heaviest lepton, and that very heft opens doors. Once those doors are open, the particle does what unstable heavy particles do. It decays. The oddity lies not in the fact that it vanishes, but in the fact that nature went to the trouble of creating such a heavy charged lepton at all, when the visible world seems perfectly content with the electron. What follows that decay is one of the reasons the tau is so scientifically valuable. It does not simply disappear into a puff of theoretical embarrassment. It decays in structured, measurable ways. The particle data group lists its branching fractions with remarkable precision. About 1 in 5 2 decays produces an electron along with neutrinos. Slightly under that goes to a muon along with neutrinos. The remaining majority is hadronic, meaning the weak decay produces quarks that then become hadrons. Atlas gives the same broad summary in simpler terms, saying that around 1/3 of taus decay to electrons or muons, and about 2/3 decay to hadrons. That hadronic majority is a big part of the tau story, because it makes the particle much harder to identify than one might wish. A lepton that often disguises itself as a narrow spray of hadrons is exactly the sort of thing experimentalists remember with admiration and mild exhaustion. It means the tau is not just short-lived, it is short-lived in a way that leaves behind signatures that must be carefully separated from more ordinary jets. Those hadronic decays also give the tau its peculiar texture in the detector. Atlas notes that the hadronic final states predominantly consist of 1 or 3 charged pions, plus a neutrino, and often some neutral pions that themselves decay to photons. This is why physicists talk about 1-prong and 3-prong 2 decays. The narrowness matters. A hadronic tau decay tends to be more collimated and more orderly than an ordinary jet produced by a quark or gluon. It often leaves a small number of charged tracks, not a busy wide spray. That is one of the clues experimenters use when reconstructing a tau candidate. Still, the resemblance to jets is close enough that the task remains difficult, and modern analyses often rely on advanced identification methods, including machine learning tools, to distinguish real hadronic taus from imposters. The mayfly is not just brief, it is brief and messy in a very specific way, vanishing before the main detector can greet it, and leaving behind a handful of footprints that look, at first glance, rather like somebody else's. There is something conceptually important hidden in that pattern. The tau teaches you very quickly that particle physics is not really about tiny marbles sitting still and waiting to be admired. It is about transitions, permissions, and lifetimes governed by the forces of nature. The tau exists as a particle, yes, but its existence is inseparable from its tendency not to remain itself. This is one reason the word lifetime in particle physics is statistical rather than biographical. The mean lifetime from the particle data group is an average over many tau decays, not a promise that each tau experiences the universe in the same tiny way. Some decay sooner, some later, but the overall pattern is extraordinarily consistent. That consistency is one of the great triumphs of the field. Even the shortest lived objects obey measurable laws. The tau does not linger, but it lingers lawfully. It does not become vague because it is brief. In a sense, its brevity is one of the cleanest things about it. Nature has decided how long a tau is usually allowed to remain a tau, and the decision is precise enough to be measured again and again. This short life also changes the emotional meaning of mass. Earlier, when we spoke of the tau as the heavy twin nobody asked for, the emphasis was on its awkward place in the family portrait. Here the emphasis shifts slightly. Weight is not merely an identity card entry. Weight is what turns the tau from a hypothetical stable cousin of the electron into a transient one. The electron cannot decay into a lighter charged lepton because there is none available beneath it. The tau sits at the opposite end of that little charged lepton ladder. It is heavy enough that the weak interaction has many kinematically allowed ways to redistribute its mass into lighter particles, so its heaviness is not just why it feels excessive, it is why it vanishes. This is such an important distinction that it is worth holding on to. The tau is not fleeting by accident. It is fleeting because nature has given it enough mass to make fleetingness possible, and once that possibility exists, the particle uses it almost immediately. That is the real meaning of being born to vanish. It is not a curse placed on the tau after the fact. It is written into what the tau is. At the same time, the tau does not vanish without leaving an argument behind. In fact, its brief life is one of the reasons it matters so much in tests of the standard model. Atlas continues to describe taus as the trickiest leptons to measure, because they do not live long enough to interact with the detectors directly. Yet, that very difficulty is also what makes them useful. Recent Atlas studies have emphasized that precise measurements of two-pair production at high energies can be compared directly with standard model predictions, and that these comparisons currently describe the data very well. That is a remarkable situation. The particle that seems least cooperative turns out to be one of the best places to ask whether the theory is still holding together under stress, because the tau is heavy, because it couples more strongly to the Higgs boson than the electron or muon do, and because many ideas beyond the standard model give special roles to third-generation particles. Every brief tau decay becomes part of a much larger interrogation. The mayfly is over almost at once, but the evidence it leaves can be made to speak for years. There is also a broader lesson here about what counts as real in modern physics. Everyday intuition loves persistence. We trust things that stay where they are, things we can point to twice, things that are still there after we blink. The tau offers a different standard. It is real not because it persists, but because its pattern of appearing and disappearing is stable across experiments. Its mean lifetime is reproducible. Its branching fractions are reproducible. Its detector signatures, however difficult, are reproducible. The offsets in decay position at high momentum are reproducible. The narrow one-prong or three-prong hadronic signatures are reproducible. In other words, the tau forces us to accept that reality at the smaller scales is often reality of behavior rather than reality of endurance. A thing can be fleeting beyond imagination and still be more firmly established than many large objects we treat casually in ordinary life. The tau is not a rumour because it vanishes quickly. It is a fact because it vanishes in exactly the ways the laws of nature prescribe. And perhaps that is why the tau remains such an oddly compelling particle. It combines extravagance with brevity. Nature gives it a mass far above the electron and muon, makes it the only lepton heavy enough to decay hadronically in this rich way, then allows it only a minuscule instant to exist as itself before converting it into other things. If you were trying to design a universe that made immediate intuitive sense, you might never write down such a particle. Yet once it is there, it begins to feel almost inevitable in retrospect, as though the universe were gently insisting that its most revealing ingredients need not be its most durable ones. The tau lives for almost no time at all, and still it manages to tell us about lepton universality, detector reconstruction, Higgs-related mass patterns, and the possibility that third-generation particles may be special windows onto deeper physics. A mayfly, in other words, but a mayfly whose wings leave equations trembling. And that makes the next question hard to avoid, because once a particle this brief can still reveal so much, one naturally wants to ask what exactly it is revealing about the universe that contains it. And that is where the tau begins to tell us something larger than its own strange biography. A particle like this does not merely reveal itself, it reveals the shape of the universe that allows it. The first thing it tells us is almost embarrassingly simple. The visible world is not the whole point of the laws of nature. CERN's own summary of the standard model puts it plainly. All stable matter in the universe is made from first-generation particles, while the heavier generations quickly decay to more stable ones. That means the world of atoms, chemistry, rocks, oceans, blood, paper, wood, and breath can be built without any lasting role for the Tao at all, and yet the Tao is still part of the rulebook. Nature has written into its deepest known theory a heavy charged lepton that ordinary matter does not need in order to become a table, a planet, or a nervous system. That is already revealing. It tells us that the universe is not arranged only around the calm, durable subset of particles that daily life happens to use. The laws are wider than the furniture they produce. They allow more than the visible world chooses to keep. That may sound like a small philosophical point, but it matters a great deal. We are naturally tempted to think that what lasts must be what matters most. Stable things feel central. Fleeting things feel secondary. The Tao politely refuses that hierarchy. It says, in effect, that a particle can be fundamental without being domestically useful. It can belong to the underlying architecture and still never become part of your teacup, your bones, or the pages of a book. This is one of the more humbling lessons in particle physics. The visible world is not a complete guide to what is fundamental. It is only the stable residue. Beneath it lies a broader set of permissions, and the Tao is one of them. Its existence tells us that the laws of nature contain more structure than is required for ordinary matter. The universe is not written to be economical at the level we first encounter it. It is written according to a deeper scheme, and the stable world is only the quietest expression of that scheme. The next thing the Tao reveals is that matter comes in families, and that this family structure is not an incidental decorative feature, but one of the deepest facts of the Standard Model. CERN describes the leptons as arranged in 3 generations, with the electron and electron neutrino in the first, the muon and muon neutrino in the second, and the tau and tau neutrino in the third. That alone would be interesting. What makes it unsettling is that the first generation already does enough to build stable matter. The second and third do not look necessary from the point of view of ordinary reality. So the Tao reveals repetition in the design of nature, and repetition in science is rarely ignored for long. It usually means one of two things. Either the theory has stumbled into a pattern it cannot yet explain, or the pattern is a clue to a deeper level of order still waiting to be uncovered. The Tao pushes us toward that second possibility. It makes the universe look as though it has a grammar below the words we already know. That family structure becomes even more revealing when we notice how similar and how different the charged leptons are. The electron, the muon, and the tau carry the same electric charge. They all belong to the lepton family. In the weak interaction, they are supposed to be treated the same way apart from tiny effects caused by their different masses. CERN summarized this in 2024 by saying that, as far as physicists know, the only difference between the lepton flavors is their mass, which comes from their different strengths of interaction with the Higgs field, while their coupling to the W boson should otherwise be equal. That is a remarkable statement. It means the universe is telling us two things at once. In one sense, these particles are equals. In another sense, they are profoundly unequal, because their masses are so different that their lives scarcely resemble one another at all. The Tao reveals that nature can preserve a deep symmetry in one part of the theory, while producing dramatic practical differences in another. The universe is more layered than a quick summary suggests. This is where the Tao becomes a window onto one of the most important ideas in modern particle physics, namely that mass is not just an amount of stuff, but a clue to how particles are connected to the Higgs field. CERN's summary of Higgs physics states that the Standard Model predicts the strength of the Higgs coupling to be proportional to particle mass, and it notes that the couplings to the heaviest fermions, including the tau lepton, have been measured. CMS likewise states that with the data collected in 2016, it was able to observe the decay of the Higgs boson to tau leptons, strengthening the case that the Higgs couples directly to fermions. The Tao therefore reveals that the Higgs is not just a boson found in a famous discovery announcement, and then placed in a cabinet. It is part of the machinery that distinguishes one generation from another through mass. The Tao matters here because it is the heaviest lepton. It is where the Higgs relation to the lepton family becomes especially visible. In other words, the Tao helps show that mass in the universe is not merely assigned. light is connected to interaction with a field that fills all space, and yet the tau also reveals that this success is incomplete. Knowing that the Higgs coupling scales with mass is not the same as knowing why the electron, muon, and tau have the particular masses they do. The Higgs framework tells us how mass is woven into the standard model, but it does not by itself explain why the tau should be so much heavier than the electron, or why there are 3 charged leptons at all. Atlas said this very directly in its 2025 tau briefing. The Higgs boson interacts much more strongly with the tau lepton than with the electron or muon, for reasons still unknown. That is an astonishingly candid sentence, and it tells us something important about the state of the field. The tau reveals both what we have learned and what we have not. It confirms that mass and Higgs coupling belong together, while also exposing the fact that the pattern of those couplings still lacks a satisfying deeper explanation. The universe, at least at this level, is willing to show us the mechanism without yet explaining the values. The tau also reveals something about how seriously the universe takes internal consistency. Because the charged leptons differ so much in mass and lifetime, one might expect the theory to begin showing cracks in how equally it treats them. But the latest precision tests do not show that. CERN reported in 2024 that new Atlas test of lepton flavor universality in W boson decays found a result perfectly compatible with unity, meaning the decay rates remain equal to extremely high precision, where the standard model says they should. That is a very strong statement. The tau looks like the unruly member of the family. It is heavy, fleeting, experimentally awkward, and dramatically unlike the electron in practical terms. Yet when one probes the weak interaction carefully, the underlying equality survives. So the tau reveals a universe that can tolerate enormous visible differences while preserving elegant regularity underneath. That is not a small insight. It means the world at its foundations may be more symmetric than the surface appearances of the particles would suggest. At the same time, this same measurement reveals something else, something almost opposite. Precision is now good enough that the tau is no longer merely a curiosity or an inconvenient cousin in the particle family. It has become a test bench. CERN described these universality measurements as sensitive probes of physics beyond the standard model. That means the tau does not just tell us about the established theory. It is one of the tools used to ask whether the established theory is the whole story. A particle once treated as an awkward extra is now one of the best places to search for tiny departures from the current rules. That is a lovely reversal. The tau reveals that in physics the most troublesome particles often become the most useful. The very fact that the tau is heavy and difficult makes it sensitive to subtle effects that lighter particles might not show as clearly. So the universe is telling us something rather cheeky here. The particles that seem least necessary to daily life may be among the most useful for discovering what the laws of nature still have not confessed. There is another thing the tau reveals, and this one has to do with energy. Atlas describes the tau as a particle seen in high-energy proton collisions, and emphasizes how difficult it is to reconstruct, because it decays before it can be observed directly as a stable track. CERN likewise notes that the tau is only seen in high-energy particle interactions. That tells us the tau belongs less to the quiet universe of long-lived structures and more to the energetic universe of collisions, creation and decay. It belongs to the kind of world that existed much more naturally in the early cosmos than in your sitting room. One must be careful here not to drift into vague mysticism about the young universe, but the basic point is solid. The tau reveals that nature includes modes of matter that become visible only under extreme conditions. Daily life is a low-energy summary. It is not the whole catalogue. To understand the universe fully, one has to understand not only what persists, but what briefly becomes possible when enough energy is concentrated. The tau is one of those possibilities, and therefore one of the signatures of a universe that is much richer under stress than in repose. The tau also reveals something deeply methodological about science itself. Because it decays so quickly, Physicists do not observe it in the simple, old-fashioned sense of watching a thing remain itself. Atlas explains that researchers must reconstruct its presence from the particles produced when it decays while removing background fakes. This means the tau is a lesson in how modern physics knows anything at all about the smallest scales. The universe does not always hand over its truths as objects. Often it hands them over as patterns of consequences. The tau reveals that what counts as reality in particle physics is not persistence but reproducibility. If the same decay products, missing energy, and detector signatures recur with the right statistical structure, then the particle is real even if it is gone almost immediately. That is not merely a technical point about one difficult lepton. It is a statement about the universe and about our way of knowing it. The deepest layers of reality are often accessible only through inference, and the tau is one of the clearest examples of that. Then there is what the tau reveals about the search for new particles and new forces. Atlas noted in 2025 that many new physics models introduce additional particles that can mix with the Higgs boson, and if that happens, those new particles often decay into the heaviest particles they can reach, very often the tau. In the same briefing, Atlas discussed studies involving 4 tau final states and other tau-rich signatures, and reported that no evidence for such new particles had yet been found. It also measured high-energy tau pair production in a way that allowed direct comparison with physics models, and the data agreed well with standard model predictions. That may sound disappointing if one likes dramatic revolutions before breakfast, but it is actually revealing in its own right. The tau shows us where many of the most plausible cracks in the current theory would first begin to show, and it also shows that those cracks have not yet widened enough to see. The universe is not being generous with shortcuts. It is making physicists earn every hint. That lack of a clean discrepancy is not a failure of the tau. It is one of the things the tau reveals most honestly. The universe may be incomplete in our description of it, but it is not obliged to reveal the missing pieces in the simplest way. One might have hoped that the heavy third generation would already be misbehaving badly enough to expose a deeper theory. Instead, the tool continues to act like a very disciplined witness. It points toward the right mysteries without openly betraying the standard model in the measurements that have so far been made. That is itself a kind of message. It tells us that the next layer of physics, if it is there, may be subtle. It may hide in tiny distortions of branching patterns, production rates, rare decays, or precision comparisons between generations. The tau reveals not only what the universe contains, but the style in which the universe gives up information. It is not reckless. It is reluctant. It leaves clues, not confessions. Perhaps most importantly, the tau reveals that the standard model is both magnificent and incomplete. CERN's descriptions of the standard model and Higgs physics make that tension very clear. The model organizes matter into generations, predicts interactions with immense success, and links mass to the Higgs field. Measurements of tau production, tau decays, and Higgs decays to tau leptons continue to support it. But the same set of facts also leaves major questions hanging in the air. Why 3 generations? Why these masses? Why does the Higgs treat the tau so much more strongly than the electron and muon? Why should the stable world be built from the first generation while the heavier generations remain part of the law without being part of the furniture? The tau reveals that our best theory is strongest where it is most precise, and weakest where it is most explanatory. It can tell us what happens with extraordinary confidence and still leave us asking why the cast list looks the way it does. So by now, the tau has done something rather impressive for a particle that never sticks around. It has shown us that the visible world is not the whole story, that matter comes in repeated families, that mass is tied to the Higgs field in a measurable way, that deep symmetries can survive beneath huge practical differences, that fleeting particles can be among the best probes of new physics, and that scientific reality at the smallest scales is often reconstructed from consequences rather than watched directly. That is quite a lot for one short-lived lepton to reveal, and yet it leaves us in a very particular mood. Not settled, not confused exactly, but aware that the standard model may be one of those grand theories that becomes more impressive and more incomplete at the same time the longer one studies it. The Tao does not simply decorate that feeling, it sharpens it. It turns a quiet suspicion into a focused one. And once that happens, the natural place to go next is to look directly at those weak spots in the current picture, because the Tao does not merely suggest that there may be cracks in the standard model, it has been standing near them all along. Once you start looking for cracks in the standard model, it is important not to imagine a ruined wall with daylight pouring through. The situation is much more awkward than that. The theory still works astonishingly well. CERN's own overview says it remains the best description of the subatomic world within its domain, and recent Atlas summaries continue to describe precision measurements and searches that so far confirm its predictive power rather than overthrow it. The cracks are therefore not dramatic failures of the sort that make a whole theory collapse in public. They are places where the theory becomes quiet, places where it tells us what happens but not fully why, and places where the universe seems to contain more structure than the theory naturally explains. The Tao sits very close to several of those places, which is one reason it feels less like a mere particle and more like a pressure point. The first crack is the one we have been circling all along. CERN states it very plainly on its standard model page. The theory does not answer why there are 3 generations of quarks and leptons with such different mass scales. That one sentence is practically the Tao's autobiography. The electron, muon and Tau are not random creatures from unrelated categories. They are a repeated family, arranged with suspicious neatness, and yet the reason for the repetition remains unexplained. The Tau matters here because it is where the pattern becomes impossible to wave away. One light-charged lepton could feel natural. A second might feel like an odd extra. A third makes the repetition structural. The standard model catalogues that structure beautifully, but it does not derive it from a deeper principle that leaves everyone satisfied. So when we say the Tau points to a crack, this is the crack most directly beneath its feet. The theory can place the Tau in the table, but it still cannot tell us why the table has this shape in the first place. The second crack lies in mass itself. The discovery of the Higgs boson and the study of its couplings were enormous triumphs, because they showed that particle masses are tied to the Higgs field in exactly the broad way the standard model expects. Atlas wrote in 2025 that Run 2 allowed Atlas and CMS to establish Higgs interactions with fermions and to observe the expected mass-dependent interaction strengths. At the same time, the Atlas Tau briefing made a point of saying that the Higgs boson interacts much more strongly with the Tau than with the electron or muon, for reasons still unknown. That combination is very revealing. We have the mechanism in one sense, but not the deeper choice of values. We know that heavier particles couple more strongly to the Higgs field. We do not know why the electron is so light, the muon so much heavier, and the Tau heavier still. The standard model gives the rule for how mass shows up once the couplings are there. It does not fully explain why those couplings take the values they do. The Tau turns that omission into something difficult to ignore, because it is the clearest heavy lepton in the family, and therefore one of the sharpest examples of the unexplained pattern. Then there is the neutrino sector, which is a crack of a more definite kind because it already tells us that the standard model, in its original form, is incomplete. CERN states this very directly in its account of neutrino oscillations. In the standard model, neutrinos have no mass, yet for neutrinos to oscillate they must have mass, which means something is missing. This matters to the Tau because the Tau is not only a charged lepton, it belongs to a family with a Tau neutrino. Once neutrinos are able to change flavour as they travel, the neat family picture becomes much less static than it first appeared. The generations are not just boxes in a chart, they participate in a deeper pattern of mixing that the standard model did not originally accommodate in a complete way. So one of the cracks near the Tau is no longer merely a matter of taste or elegance. It is a confirmed gap. Nature has already told us that the lepton story is incomplete, and the tau family is part of that unfinished business. A fourth crack appears when we stop looking only at the laboratory and look at the universe as a whole. CERN says the standard model does not explain what dark matter is, and its dark matter page notes that the matter we know, the matter in stars and galaxies, accounts for only a small fraction of the universe. The exact point for our purposes is simple. The beautifully measured particles of the standard model, including the tau, do not explain most of the matter content inferred from the way galaxies and larger structures behave. That means the standard model is not the full inventory of reality. It is a highly successful theory of visible matter and known interactions, but not a complete theory of the cosmos. The tau becomes relevant here not because it solves dark matter, but because heavy leptons and third-generation particles often appear in models that try to go beyond the standard model. Atlas noted in its 2025 tau briefing that many new physics models introduce extra particles that can mix with the Higgs boson and then often decay into taus. The tau therefore sits near the boundary between what is established and what is still being searched for. It does not fill the dark matter gap, but it often becomes one of the places where new ideas about that gap are tested. The matter-antimatter problem adds another fracture, and this one is especially uncomfortable because it concerns the very fact that anything solid exists to ask the question. CERN explains that if matter and antimatter were created and destroyed together in the early universe, one would expect nothing but leftover energy. Yet a tiny surplus of matter survived, roughly 1 particle per billion. CERN also notes elsewhere that the standard model cannot adequately explain the observed abundance of matter in the universe. That is a very serious gap. It means the theory that describes known particle interactions so well still cannot fully explain why the universe contains stars, planets, bookshelves, and sleepy people listening to particle physics at odd hours, rather than a blaze of balanced annihilation. The tau enters this story more indirectly than in the flavor problem, but still meaningfully. Whenever physicists suspect that new sources of asymmetry may exist beyond the standard model, the heavier generations of matter become natural places to investigate, because they are the ones most likely to reveal new interactions or hidden patterns. The tau, as the heavy charged lepton of the third generation, keeps showing up near that frontier. There is also the crack that comes from gravity's absence. CERN's standard model overview says gravity is not part of the theory, and that fitting quantum theory together with general relativity into a single framework has proved very difficult. One can become so used to this sentence in popular explanations that it begins to sound routine, but it is not routine at all. It means our best theory of particles omits one of the fundamental forces of nature. Of course, gravity is negligible for the tiny processes inside particle detectors, which is why the standard model works so well for what it was built to describe. But a mission is still a mission. The tau matters here in a quieter way. Because it is such a well-measured member of the matter sector, it reminds us how far the standard model can go, while still being only partial. You can know an extraordinary amount about a particle, and still not possess the final theory of nature. In that sense, the tau reveals a philosophical crack as much as a technical one. The theory is powerful enough to describe its decays and interactions in detail, yet not broad enough to join the quantum world seamlessly to the gravitational one. Then there is the Higgs naturalness problem, which is a slightly more delicate subject because it depends on what kind of theoretical discomfort one is willing to take seriously. CERN and Atlas both describe it in cautious but unmistakable language. CERN's overview of searches beyond the standard model explains that according to quantum mechanics, the Higgs boson should receive very large contributions to its mass from virtual particles, and the Atlas Run-To feature speaks of puzzling fine-tuning in the scalar sector, and notes the non-observation of new TV-scale particles despite strong theoretical motivation. This is the kind of crack that does not come from a direct contradiction between data and theory. It comes from the sense that the observed Higgs mass looks surprisingly delicate, unless some deeper structure stabilizes it. For years, many physicists hoped that supersymmetry or something similar would appear at the Large Hadron Collider and tidy up that problem. But the same Atlas feature says that no compelling evidence of new physics has yet emerged, even as searches have pushed exclusions higher and higher. The 2 enters here because it is one of the particles most strongly connected to the Higgs among the leptons. If the scalar sector is where the standard model feels most delicately balanced, the tau is one of the clearest fermionic witnesses to that balance. What makes all this more interesting, and in a slightly mischievous way more difficult, is that some of the supposed cracks turn out not to be cracks after all, at least not yet. That is part of the current story too. In recent years, several anomalies in flavor physics led people to wonder whether lepton universality might be starting to fail. Atlas said in 2025 that one of its 2 studies was motivated in part by anomalies seen in hadron decays by the LHC-b experiment. But the same briefing reports that no evidence for the new particles in that search was found, and that high-energy tau pair production agreed well with standard model predictions. Likewise, CERN reported in 2024 that Atlas measured a ratio for W boson decays to muons versus electrons of 0.9995 with an uncertainty of 0.0045, perfectly compatible with unity. That is an important lesson in itself. The standard model's cracks are not places where every intriguing hint becomes a discovery. Sometimes the wall looks weak from a distance. You walk over, tap it carefully, and it turns out to be annoyingly solid. The tau has been part of that story too. It is not only a signpost toward new physics, it is also one of the best tools for showing how stubbornly the old physics still holds. This is why the mood around the standard model has become so peculiar. On the one hand, it is incomplete by the theory's own admission. CERN says outright that it leaves gravity out and does not answer dark matter, the fate of antimatter after the Big Bang, or the reason for the 3 generations. On the other hand, Atlas keeps reporting precision measurements and broad searches that confirm the model again and again. The result is not triumph or failure, but tension. The cracks are real, but they are not widening in the convenient places. The most dramatic hoped-for extensions, at least at accessible energies, have not yet shown themselves clearly. Heavy extra particles have not politely walked into the detectors. Supersymmetry has not arrived on schedule. Additional Higgs bosons remain unconfirmed. The tau, meanwhile, keeps behaving exactly enough like a standard model particle to preserve the theory's dignity, while remaining strange enough to preserve our unease. That leaves us with an odd but very productive state of mind. The cracks in the standard model are not random. They cluster around very specific questions. Why this family structure? Why these masses? Why do neutrinos have mass? What is dark matter? Why does matter dominate over antimatter? How does gravity join the picture? Why does the Higgs sector look so delicately poised? The tau touches several of those questions at once. It sits at the sharp end of the lepton mass hierarchy. It belongs to the mysterious 3rd generation. It couples more strongly to the Higgs than the electron or muon do. It appears naturally in many searches for new particles that might extend the standard model. And yet, whenever we ask it to testify, it speaks in a slightly maddeningly disciplined voice. It says, yes, the theory works here too. Yes, the rates match. Yes, the decays balance. Yes, the universality tests still hold. It points to the cracks without prying them open. Perhaps that is why the tau remains such an effective guide through this part of physics. It does not let us become lazy. A genuine disaster for the standard model would be easy to narrate. A perfectly serene completion of the theory would be easy as well. The tau offers neither comfort. It is too strange to feel fully explained and too obedient to serve as an outright rebellion. It keeps the theory under pressure by existing in exactly the way the theory permits, while still embodying several of the theory's most unresolved features. And that means that when we finally come back to the simplest question, the almost childish one of what kind of particle this really is, we're no longer asking only for a label from the particle zoo. We're asking what it means that the universe contains something so lawful, so brief, so heavy, and still so conceptually inconvenient, which is why, after all these cracks and all this careful bookkeeping, the strangest thing about the Tao is still the oldest thing we noticed about it. It should not feel this necessary to the laws of nature, and yet there it is, very much included. And so we come back to the Tao in the only way that really feels honest, which is not as a solved thing, not as a tidy fact at the edge of a textbook, but as a small and stubborn reminder that the universe is under no obligation to arrange itself according to our sense of neatness. The Tao is here. That is no longer in doubt. It has been measured, reconstructed, compared against theory, woven into the standard model, and studied in increasingly careful detail for decades. The standard model itself places the Tao in the third generation of leptons, alongside the electron and the muon, while CERN describes the first generation as the lightest and most stable, and the heavier generations as less stable. In other words, the theory does not reject the Tao at all. It includes it very calmly. The discomfort comes afterward, when one notices that inclusion is not the same thing as explanation. The Tao belongs, and still feels strangely unearned. That is why the phrase "the particle that should not be here" has never really meant forbidden. It has meant unnecessary in the narrow sense and revealing in the deeper one. Ordinary matter is built from the first generation. CERN says that all stable matter around us is made from elementary particles, and that the lightest generation is the one that forms the durable world we know. The heavier generations decay down to more stable ones. That means the visible universe of atoms and chemistry does not require the Tao as a lasting ingredient. You can have stars, oceans, stone, skin, paper and breath without any stable Taos taking up residence inside them, and yet the laws of nature still contain one. That is the point. The Tao reveals that the rulebook of the universe is larger than the calm, survivable subset from which everyday reality is assembled. The laws contain more than the furniture. Once you see that, the Tao becomes less like an odd extra and more like a witness. It tells us that matter is organised into repeated families, and that this repetition is one of the deepest unresolved features of modern particle physics. CERN describes the quarks and leptons as coming in 3 generations. The pattern is orderly enough to look intentional and mysterious enough to remain unsettled. One charged lepton might feel natural, 2 might feel like a curiosity, 3 begins to look like a clue. The electron, muon and Tao are not random strangers. They are versions of a pattern nature has chosen to repeat, and the standard model, brilliant as it is, still does not explain why the repetition stops at 3, or why the masses spread so dramatically from one family member to the next. The Tao, sitting at the heavy end of the charged lepton line, is where that question begins to feel impossible to ignore. There is something especially sharp about the Tao because it is both familiar and excessive. It carries the same electric charge as the electron. It belongs to the same lepton family. In the weak interaction, the basic rule is that the electron, muon and Tao should be treated the same way apart from the effects of their different masses. CERN summarised this in its discussion of lepton flavor universality, and recent Atlas work continues to support that principle with high precision. So the Tao is not rebellious in the obvious sense. It does not barge into physics shouting that the standard model is broken. It obeys the formal rules almost irritatingly well. And yet its mass is so much larger, its life so much shorter, and its practical role so much stranger than the electrons, that it still creates the strong impression that there is some deeper layer of explanation missing. It behaves correctly while making the theory feel unfinished. That unfinished feeling becomes even stronger when the Higgs enters the story. CERN and Atlas both emphasize that the Higgs interaction strength scales with particle mass, and Atlas has noted that the Higgs interacts much more strongly with the Tau than with the electron or muon. CMS has also highlighted the observation of Higgs boson decays to Tau leptons, strengthening the evidence that the Higgs couples directly to fermions and not only to force-carrying bosons. This is one of the great successes of the Standard Model. It means the tau is not merely a heavy cousin with no formal significance. It sits at the place where the relation between mass and the Higgs field becomes especially visible in the lepton family. But the same success turns back into a question almost immediately. We can say how the Higgs relates to mass within the theory, yet we still do not know why the tau has the particular mass it does, why the electron is so much lighter, or why the whole family pattern exists in this exact form. The tau therefore reveals both the triumph and the limit of what we currently know. And then there is its brief life, which changes the emotional texture of the whole particle. The tau is not simply heavy. It is heavy in a way that gives it many available exits. That is why it vanishes so quickly into lighter particles. Atlas describes taus as the trickiest leptons to measure because they do not live long enough to interact with the detector directly as stable charged particles. Physicists have to reconstruct them from the particles they produce when they decay, carefully filtering out backgrounds that mimic the same signatures. This matters because it means the tau is not only a conceptual problem, it is also an experimental challenge, and the challenge is inseparable from its physical character. It is a particle whose reality is known through structured disappearance. The universe permits it briefly, then takes it apart according to rules precise enough that its absence can be measured almost as reliably as a presence. That kind of particle does something unusual to one's picture of the universe. It teaches that persistence is not the same thing as importance. A stable electron helps build your body and your walls and your wiring. A tau does none of that, and still it may be one of the most revealing members of the particle family. Atlas has stressed that taus are especially valuable in searches for new physics, because many extensions of the Standard Model give a privileged role to the heaviest particles, and the tau is the heaviest lepton. If new particles mix with the Higgs boson, they often prefer to decay into the heaviest accessible matter particles, which frequently means taus. So the tau is strange in a very specific way. It looks unnecessary from the point of view of daily matter, and yet it becomes highly useful from the point of view of deeper theory. The universe does not use it to make chairs or lungs, but it may yet use it to tell us where the current theory gives way to a broader one. This is where the tau becomes almost philosophical, without ever ceasing to be technical. It reminds us that a theory can be magnificent and still incomplete. CERN says plainly that the Standard Model does not answer why there are 3 generations, does not explain dark matter, does not fully account for the matter-antimatter imbalance, and does not include gravity. That is a remarkable list of absences for so successful a theory. The tau stands near several of those absences at once. It belongs to the unexplained family structure. It participates in the unexplained mass hierarchy. It sits in the 3rd generation, which many theorists regard as especially promising terrain for new phenomena. It does not cause the Standard Model to fail in public, but it does quietly accompany some of the places where the theory stops answering the deepest questions. There is also something deeply instructive in the fact that the tau has not yet betrayed the Standard Model outright. One could imagine a more theatrical particle, one that produced glaring anomalies at every turn and forced physicists to rewrite the theory in a week of panic and very expensive coffee. But that is not what has happened. Atlas reported in its recent tau briefing that measurements of high-energy tau pair production agree well with Standard Model predictions, and CERN noted that new precision tests of lepton flavor universality remain compatible with the expected equality of couplings. That means the tau is not the kind of clue that solves itself. It points. It does not confess. It suggests that something deeper may be there without yet announcing exactly what that deeper thing is. The universe, in other words, is not being careless with its mysteries. It is giving us particles like the tau lawful enough to preserve the old theory and strange enough to prevent complete comfort with it. One begins to suspect after a while that this is one of the ways nature prefers to work. It does not always hand us dramatic contradictions. Sometimes it hands us structures that are too regular to be accidental and too unexplained to be final. The tau belongs exactly to that category. It is not like dark matter, which is inferred from the cosmos and not yet pinned down as a particle in the laboratory. It is not like a speculative boson that may or may not ever appear. The tau is already here, already measured, already built into the official account. That makes it more troubling in some ways, not less. A confirmed particle that still feels conceptually odd is a harder thing to dismiss than a hypothetical one. The tau is not a future puzzle, it is a present one, and perhaps that is why it has such a special place in this story. The electron feels inevitable because we live inside the world it helps build. The muon feels surprising but still somehow manageable, a heavier cousin that already taught physics not to assume too much. The tau is where the pattern takes on real weight, literally and intellectually. It is the point at which repetition becomes structural, heaviness becomes revealing, and short life becomes a scientific advantage instead of a mere inconvenience. It is the relative who arrives late, says almost nothing, leaves immediately, and somehow changes the atmosphere of the entire room. The standard model does not collapse in its presence. It simply starts to feel like a theory that knows more about procedure than about motive. There is a quiet tenderness, too, in the fact that the tau tells us so much while remaining so brief. It never becomes part of the ordinary world in the durable sense. It does not help hold your cup together or carry current through the wire beside your bed. It lives in violent collisions and then departs. But during that departure it says several very important things. It says that the visible world is not the whole inventory of the laws beneath it. It says that matter comes in generations whose pattern remains unresolved. It says that mass is tied to the Higgs field in a measurable and meaningful way. It says that symmetry can survive underneath enormous practical differences. It says that fleeting particles can be some of the best tools for testing deep theories. And it says, perhaps most of all, that explanation in physics often trails behind description by a very long distance. So, what is a tau particle really? It is a charged lepton of the third generation. It is the heaviest lepton we know. It is a particle whose interactions and decays fit the standard model with impressive discipline. It is a place where the Higgs relation to mass becomes sharply visible. It is a difficult experimental object and a useful one. It is part of a repeated family pattern that still lacks a satisfying ultimate explanation. It is one of those rare scientific things that becomes more unsettling, not less, as the measurements improve, and that is why it should not be here in the deeper emotional sense. Not because it is impossible, but because it still feels like the answer to a question we have not quite learned how to ask properly. By the time one reaches that thought, the tau has become more than a strange item in particle physics. It becomes a kind of test for how we think about understanding itself. Are we satisfied when a theory can predict outcomes with astonishing precision, even if it leaves the family structure of matter unexplained? Are we content to know how the tau behaves without knowing why the universe wanted such a particle in the first place? Can a theory be called complete if it includes a heavy third-generation lepton, describes it beautifully, and still has no final answer for why there should be 3 generations at all? The tau keeps those questions alive. It refuses to let success become complacency. It reminds us that one can have an excellent map and still not know why the country has this shape. And perhaps that is the fairest way to leave it. Not with a grand declaration that the tau has solved the mystery of the universe, because it has not, and not with a tidy reassurance that it is only a specialist detail because it is not. The tau is one of those small facts that tilt the room. It is lawful, measurable, official, and still somehow improbable in spirit. It belongs to the universe we have, not the one we might have designed for convenience, and in that sense it may be one of the most honest particles in physics. It tells us that reality is under no pressure to be minimal, that the deeper rulebook is broader than the world of stable matter, and that sometimes the most revealing things are the ones that arrive briefly, obey every formal rule, and still leave behind the unmistakable sense that the story underneath them has not yet been fully told.